you. Yeah. Sorry, I got little late.
No, I think it is time only.
Yeah, we can start.
Okay, afternoon session. Professor Balish Kumar from IIT Europa will talk about modular functions on the complex upper half plane and three-dimensional hyperbolic space. Okay, please go ahead.
Thank you, Professor Baer, for the nice introduction. And I would like to thank the organizers for giving me this opportunity to talk in this conference. So the title of my talk is on modular functions on the complex upper half plane and three-dimensional hyperbolic space. So this talk consists of two parts. So initially we will be discussing certain connections between modular functions on the complex upper half plane and a product of complex upper half plane. Two copies of complex upper half plane and one copy of complex upper half plane. And we will see certain interaction between modular forms in one in single copy of upper half plane and two copies of upper half plane. And the second part of the talk will consist of modular function on the complex upper half plane and three-dimensional hyperbolic space. Yeah, so certain connections we will see. And these two connections is based on basically the first non-trivial extension of Q, namely the real quadratic field and imaginary quadratic field, respectively. Yeah, so before starting, let me fix the definitions and notations. So here SL2Z, as usual, denotes the set of 2 cross 2 matrices with integer entries and determinant 1. And so this SL2Z, in fact SL2R, acts on the complex upper half plane by this Mobius transformation. So if you take SL2Z matrix gamma and it acts on Z as A plus B over C Z plus D. And a function is from complex upper half plane to complex plane is said to be a modular form of weight parameter K is an integer, or the modular SL2Z is a so-called modular group if it satisfies this transformation property with respect to this weight K. F of gamma Z is this automorphy factor Cz plus D to the power K F of Z, and this function should have at most polynomial growth. So if you take imaginary part going to infinity, then the behavior of the function should be bounded by this polynomial in y to the power some constant alpha. Yeah. So the very first example for weight k greater than 2, one can see that this Eigenstein series is a modular form of weight k for SL2Z. And similarly, so this since this modular form is invariant under the action of the matrix 1 1 0 1, so therefore one can see that it is translation invariant, and one can write down the Fourier expansion of this modular form as A0 plus summation n from 1 to infinity a and e to the power 2 pi I and z. Here z is a complex number which that is in the upper half plane. And this Fourier series starts from the non-negative indices 0 onwards. And so this is the Fourier series expansion, and ANs are known as the Fourier coefficients. And we say that F is a cusp form of weight K for the modular group SL2Z if the very constant term vanishes. So this is the one can say the value of the function F at the I infinity, and it should vanish at the infinity. Yeah. And the famous example this of cusp form, the very first, one should say the first example of cusp form is the Ramanujan delta function, which is defined in terms of the Eigenstein series of weight here 4 and Eigenstein series of weight 6. So G2 corresponds to Eigenstein series of weight 4, and G3 corresponds to the Eigenstein series of weight 6. And so they are scaled, they contain certain factors 60 and 140. Yeah? So it turns out to be a cusp form of weight 12 for the full modular group. So let me fix certain notations that the space of all cusp form of weight k for the modular group SL2Z forms a complex vector space, and we denote it by SK SL2Z, in fact, finite dimensional complex vector space. Yeah, and so there is a family of operators acting on this space is known as Heke operator for each positive integer n. So we have Heke operators acting on the space of cusp forms. In fact, it acts on the space of modular forms, but for the purpose of this talk, we will be fixing our notations for the cusp forms. So we have this family of Heke operators acting on this space, and this is given explicitly in terms of this definition. Yeah, and so we have a family of Heke operator acting on the space, and so the spectral theory of these finite dimensional vector spaces will tell you that one can get a simultaneous Heke eigenform for each Heke operator, and the definition we say that f is a Heke eigenform if this function f is an eigenvector for each operator Tn. Yeah, and moreover, it turns out that the very first Fourier coefficient of Heke eigenform turn out to be non-zero, and once we normalize and we by dividing it, and we say that the Heke eigenform is normalized if the very first Fourier coefficient is equal to 1. And in this case, it turns out that this eigenvalue actually coincides with the Fourier coefficients of modular form. So similar way, one can define the congruent subgroups of SL2Z by certain congruence condition that the third entry of the SL2Z matrix should be congruent to 0 modulo n. Yeah, and one takes another parameter, this Dirichlet character chi for a positive integer m, and so then one can in a similar way define the modular form of weight k with label n and character chi, and so we denote this as sk and chi. So far what we have defined the modular form for SL2Z, and since as I told in the very beginning that this will be sort of interaction of this integers z and the, which one can think of as the ring of integer for the rational numbers, and so and the first non-trivial extension of rational numbers is the quadratic extension, and so this will be an interaction of certain modular function for SL2Z and modular function for the quadratic extensions of Q. Yeah. So let me just fix the notation for real quadratic field. So here d, small d, be a square free integer, then we form a real quadratic field. And the discriminant we will denote it by capital D, which is small d if d is 1 mod 4, and in other case it is 4 times d. And the ring of integers of this k is denoted by O. And so for the simplicity, we will also assume that this real quadratic field is of class number 1. And so here an element inside the real quadratic field, we will denote A dash is the conjugate of A inside the real quadratic field Q. And then one considers the Hilbert modular group corresponding to this real quadratic field is SL2O, which is the set of 2 by 2 matrices with entries from the ring of integer and the determinant. Yeah. So with respect to this, so one can see that this SL2O actually acts on the 2 copies of upper half plane, namely H cross H, and the action is given just if you take SL2O matrix, and if you action is given by gamma times Z1 Z2 is just a component-wise bilinear this Mobius transformation action. And so one second component will correspond to conjugate of A dash, here denotes the conjugate of A. Similarly, B dash is the conjugate of B, and so on. So the first component corresponding to the first corresponding to the trivial this thing, and the second one corresponding to the conjugate of this K. And so one defines a Hilbert modular form of weight K1, K2 inside inside this Z cross Z. Here weight will be K1 and K2, and for the full Hilbert modular group SL2O, if it satisfies the transformation property, and moreover the growth condition in this case can be relaxed because there is a theorem which goes back to the name of Gauss-Kosher principle, which says that if you have non-trivial extensions, and if you look at Hilbert modular form, which is holomorphic and satisfies this transformation property, then it will automatically be a, say, polynomial group. Yeah. So, and in the case of parallel, so when K1 and K2 are same, then we say that the Hilbert modular form is a parallel with K. And so similarly, as in the case of SL2Z, one can construct examples of Hilbert modular forms like Eigenstein series, Hilbert Eigenstein series, and Cus forms also. And so here also we have this Fourier expansion because it is also invariant under the translations. And so the Fourier expansion of a Hilbert modular form is given as A naught plus summation over the elements of the inverse different. Here delta inverse is the inverse different inside the real quadratic field K. And so nu greater than 0 means nu is totally positive. That means nu and its conjugate nu dash both are positive. And A nu times e to the power 2 pi I nu z1 plus nu dash z2. Yeah. And one says that the Hilbert modular form is the Hilbert Cus form if the very constant term vanishes. Yeah.
There is a question in the chat box.
Okay. Okay. So can you just read the question because I am not able to.
C prime and D prime.
Sorry.
C prime and D prime are the conjugate of C and D.
Yeah, yeah. This dash denotes the conjugate of this inside the real quadratic field K. So we have these two embeddings. So one is the trivial identity embedding, another one is the conjugate here. Yeah. So so in a similar way, one can, and so there is an action of family of AK operators on the space of Hilbert Cus form, and one can similarly define normalized Hilbert AK eigenform as well in this case also. And similarly, one can set up the notations corresponding to the congruent subgroup of SL2O, and one defines the what to say SK gamma naught NO is the space of Hilbert Cus form of weight K for gamma naught N, and so similarly they will also form a finite dimensional complex vector space. And okay, so what we have defined two types of modular forms on complex upper half plane and two copies of complex upper half plane. And naturally, we know that the integer sits inside the real quadratic field, and so therefore SL2G sits inside SL2O, where O is the ring of integer of real quadratic field. And one is interested to study how, and we also know that how the integer sits inside the real quadratic field. And so let us just try to set up the things in order to motivate what we are going to discuss. So given a real quadratic field or quadratic field, one can attach an analytic object, so-called Dedekind zeta function, which is defined in terms of a norm of an integral, non-zero integral ideals, where some run towards this non-zero integral ideals. And this series makes sense for real part of s bigger than 1. And so therefore this is well known that this Dedekind zeta function can be analytically continued to the whole complex plane, and it has a simple pole because of coming from the Riemann zeta function, which is defined as zeta of s is summation and from 1 to infinity n to the power minus s. And then one can also define so given a real quadratic field, one can have a Dirichlet function attached to it corresponding to the Kronecker symbol or Dirichlet symbol, Dirichlet character, whatever we say, which is defined as Ls chi d of n to the power minus s, where n runs from 1 to infinity. And this chi d of here is defined for z mod dz star, but one can extend it to z integers, and this is defined in this way. Yeah. So it takes value 1 if it is square mod d and co-prime to d, and minus 1 if it is non-square modulo d, and 0 otherwise. So we have three zeta functions are Dirichlet L function, Dedekind zeta function, Riemann zeta function, and this Dirichlet L function. And the very interesting fact is that the Dedekind zeta function factors as Riemann zeta function and Dirichlet L function. And for real part of s bigger than 1, one can see that this Dedekind zeta function has an Euler product, and this Riemann zeta function has an Euler product, and this Dirichlet function has an Euler product. And so therefore each one has Euler product, and one can compare the Euler factors on both sides. And if one compares the Euler factors on both the sides, then one can see that how these rational primes are rational, what to say, the prime integers inside Z, how they decompose or how they sit inside the real quadratic field. Yeah. So by comparing the Euler factors, one can see that either this rational prime will stays as a prime inside real quadratic field, or it is splits in the product of two prime ideals, or it is this rational prime is a square of some prime ideal inside the real quadratic field. Yeah. So therefore this captures the information that the integers sits inside the real quadratic field in this way, which is captured by this nice Dirichlet L function identity. Yeah, and therefore naturally one would like to ask the question that how this modular form for SL2G sits inside the modular form, Hilbert modular forms for the real quadratic field. Yeah. So for this one, so since we are talking about in terms of L function, so we also have an L function attached to the this modular form. So normalized Hecke eigenform, if we take inside Sk of SL2Z, then one can define this L function LSF, which is defined as an n to the power minus s, where an's are the Fourier coefficient of this normalized Hecke eigenform. And similarly, one can define the twisted L function of f by the character chi d. Here chi d corresponds to the character coming from the real quadratic field K. And one just twist the L function LSF by this chi d of n. And also we have a L function attached to this Hilbert eigenform for the full Hilbert modular group SL2O. And this is also defined as what to say, non-zero integral ideals. And C of A denotes the Fourier coefficients corresponding to this integral ideal divided by norm of A to the power S. Okay, so we have again 3L function corresponding to two different modular forms. And so in 1969, K. Doi and Naganuma had shown that how to construct a Hilbert eigenform so that the standard L function attached to f hat satisfies the identity that LSF hat should be factoring as LSF times LSF tensor chi d. Yeah. So this is the question addressed by Doi and Naganuma. And so in this case also we have a nice Euler factors. And so if one writes the Euler product of both the sides and compare the Euler factors, then one can actually deduce the Fourier coefficient of this Hilbert Hecke eigenform. Yeah, so Cp corresponding to each prime p, if one compare the Fourier coefficient, if one compare the Euler factors, then one can see that Cp will be exactly equal to A suffix rational prime p if p splits, or AP square minus 2 times p to the power k minus 1 if p is inert, and Cp is exactly A times AP if p ramifies. Yeah. And since we are demanding the condition that this f hat should be a Hecke eigenform, Hilbert Hecke eigenform, therefore it should satisfy the Hecke relation that C of prime power is should satisfy the similar Hecke relation. And in this way, one can find the Fourier coefficient for prime powers. And since we are talking about decay eigenform, so therefore the Fourier coefficients are multiplicative, and by the multiplicativity we will be able to know the Fourier coefficient of the Hilbert decay eigenform, provided such a f hat should exist. Yeah, if such a f does exist, then we will explicitly know the Fourier coefficients of that Hilbert decay eigenform. And yes, such a Hilbert cusp form or Hilbert decay eigenform exists. That's the main thing that K. Doi and Naganuma proved, and they proved it by proving a converse theorem of Weyl in the context of Hilbert-Marlowe forms. And this converse theorem of Weyl essentially says that if one has nice analytic properties of certain Dirichlet series, namely it should have analytic continuation to the whole complex plane, it satisfies the functional equation, and this function should be bounded in vertical strips, then in fact,
Lalit.
yeah.
So if had
Excuse me, there is one more question in the chat.
Okay.
It asks, f hat has weight kk.
Yes, it is of parallel weight kk. Yes, if we start with a weight k, elliptic modular form or modular form for SL2Z, then f hat will be a parallel weight kk.
Okay, thank you very much.
So this is the existence of such a f hat is proved by proving the converse theorem of Weyl in the context of Hilbert-Marlowe forms, and converse theorem of Weyl essentially says that if one has nice sufficient analytic properties of the Dirichlet series, namely it should have a analytic continuation to the whole complex plane, it should have functional equation, and it should be bounded in vertical strips, then one can in fact prove that the coefficient of the Dirichlet series is in fact coming from Marlowe form coefficient. Yeah, so using that thing, they proved that such a Hilbert decay eigenform do exist. And subsequently, so far what we have seen that if we start modular form of label 1 for SL2 corresponding to SL2Z, then one can get a Hilbert-Marlowe form for the full Hilbert-Marlowe group. So label 1 can be lifted to label 1. So after 1 year, H. Naganuma also find a lifting. So from SK of D, SK D chi D, if you take a modular form of weight K with label gamma naught D, here D is the discriminant of real quadratic field, and chi D is the character corresponding to the real quadratic field. So if you take Hecke eigenform, normalized Hecke eigenform of weight K, label D with character chi D, then he showed that can also be lifted to a label 1 Hilbert eigenform. Yeah, and the proof is essentially same as exploiting the converse theorem of Weyl in this case as well. So therefore, what we see from here that this modular form for SL2Z can be lifted inside the Hilbert-Marlowe form corresponding to real quadratic field in 2 ways. So one from label 1 should go, label 1 goes to label 1, and parallel weight kk here, sk of SL2O, that means here k is a parallel weight kk. And label D with character chi D will also be going to the label 1 Hilbert-Marlowe form. Yeah, and therefore one is asking then that what are all modular forms for the congruent subgroups of SL2G which can be lifted to label 1 Hilbert-Marlowe form. And therefore this is a nice result of Ghate, which essentially says that up to twist by these characters like this chi D, so we can only have sk of n chi is either label 1 or label D with character chi D. Yeah. So therefore, this result of Ghate says that if you take this any label n, any character chi, and weight k, if it is lifted to Hilbert-Marlowe form of label 1, then this n should be either 1 or n will be equal to D, and then chi will be equal to chi D. Yeah. And so in 1975, Zagier also studied this Doi-Naganuma lifting, and he obtained the explicit image of any cusp form inside explicit image of any cusp form of weight k label d with character chi d. So just remember that this Doi-Naganuma lift a priori is defined in terms of Hecke eigenforms. And here, Jaeger studied this Doi-Naganuma lifting directly for any general cusp form. And he studied just by giving the explicit image of any cusp form, and the image is given explicitly by computing the Fourier coefficient. So his way of understanding this Doi-Naganuma lifting is in terms of directly Fourier coefficient, which doesn't depend a priori on Hecke eigenforms. And so what he studied, he took this lifting, this SKD chi d, and which goes to SK of SL to O. Then Zagier studied that if you give me any general cusp form in SKD chi d, I can give you the direct image of this Doi-Naganuma lifting, which a priori doesn't depend on this Hecke eigenform, which will be encoded in terms of the Fourier coefficient of the form that we have started with. And Kudla mentioned that this lifting, Doi-Naganuma lifting, can be also generalized to general arbitrary label and characters, but he did not give the explicit proof. And so what in our first work, what we did, that we have generalized this Doi-Naganuma lifting for label arbitrary for general label and with certain characters. So the result with Manikam in 2016, what we have proved that if you take the square free integer m, and if you look at the real quadratic field with discriminant capital D, and if we know that this capital D divides this square free integer m, then one can in fact find a linear map. Moreover, so let me just say that moreover, this Zagier also proved that the lifting that he constructed is Hecke equivariant. That means this lifting, which is directly given in terms of general cusp form, is actually Hecke equivariant. That means it commutes with the Hecke operator. So one can generalize this lifting to label, that if you take label m with character chi d, that can be lifted to the Hilbert-Mulder form of parallel weight k, and the label will be m by d here. So here n is m by d. So therefore, and this fits in the case of this here what we have, that label d goes to label 1. So corresponding to this, what we have proved, that if you take general label m with character chi d, that will go to label m by d. And we have given explicit, if you take general cusp form here, then we have given the explicit Fourier, this f hat, this lifting is given in terms of Fourier expansion, which is explicitly encoded in terms of small f. Yeah. And these notations are just this suffix below corresponds to the index of the Fourier coefficient, and d1n corresponds to the Fourier coefficient of f at the cusp d1n. Yeah, so this is certain complicated notation, and so this is generalized for label d with character chi d to label m with character chi d, and this can be lifted into label m by d. The Hilbert-Mulder form. Yeah, and moreover, what we proved that in fact this lifting also satisfies the spirit of Doi-Naganuma lifting, that this, if you look at the lifted form, and if you look the L function of the lifted form, this factors as LSF times LSF bar s, which is F bar is here the conjugate of the L function LFS, just by putting conjugate of this coefficients of F. Yeah, so this is the result, and moreover in 2019 we have also generalized the analog of label 1 goes to label 1. So here what we have is SK of SL to Z goes to SK of SL to O. That means here label 1 goes to label 1. So in this case what we have generalized, that in fact label N goes to label N. So if you give me level n elliptic modular form or modular form for gamma 0n of weight k, that can be lifted to the Hilbert modular form of level n with parallel with k. And again, this Fourier, lifting is given in terms of Fourier coefficients explicitly. Yeah, and moreover, in this case also we proved that this satisfies the this Dai-Naganuma description that the L function of the lifted form factors as the L function that we have started with times Ls F tensor chi. Yeah, and so these are the things. So let me just for the time being skip the proof of idea of the proof of the results, and in the last we will be discussing the final proof of the results that will combine the real quadratic field, and idea in fact will be the same for real quadratic as well as imaginary quadratic. So let me now move to the imaginary quadratic field. So what we have seen that in the case of real quadratic field, we have a nice interaction of this modular form for SL2Z and modular forms for SL2O Hilbert modular group. And now one is interested to study this whether there is a connection corresponding to the modular form for complex upper half plane and modular forms which corresponds to the Bianchi modular group. Yeah, SL2O, where O corresponds to the ring of integer of imaginary quadratic field. Yeah. So let me start first a bit motivation, and then we will come to our actual theme of the title of the talk. So if we again here K, again I am denoting by abuse of notation, K here will be an imaginary quadratic field now of discriminant small d. And so given again this imaginary quadratic field, one can attach an analytic object, namely Dedekind zeta function, which is again defined in terms of this 1 over norm of a to the power s, where a runs for non-zero integral ideals. And this series converges absolutely for real part of s bigger than 1. And therefore, one can rearrange the terms and one can write this Dedekind zeta function as a partial zeta function, where sum runs over the ideal classes in the ideal class group, and zeta k of SA is the partial zeta function corresponding to this ideal class A. Yeah. So therefore, this Dedekind zeta function can be written as sum of partial zeta function for real part of s bigger than 1. And with some effort, one can in fact show that this partial zeta function can be again interpreted in terms of certain factors 2 over omega, where omega is the number of units inside the imaginary quadratic field K. And here zeta 2s is the corresponding to the Riemann zeta function. And here EZAS, so ZA, so if you give me ideal class, one can associate a point in the complex upper half plane. So that point is denoted as ZA. And so this ZA is associated to the ideal class A. And so this is usually known as CM point. And so EZAS is the Eigenstein series, which is defined as in terms of Eigenstein series. Here, summation runs over co-prime integers. YA is the imaginary part of ZA to the power s, absolute value of m plus n times ZA to the power minus 2. And this EZAS is known as Eigenstein series, are known as mass forms of weight 0 for SL2. So that mass forms definition we have seen, I think we have seen in the morning lectures. So here, so therefore this partial zeta function is in fact Riemann can be interpreted as Riemann zeta function times Eigenstein series. Yeah, and this Eigenstein series is a modular object, namely it is a mass form of weight 0 for the full modular group SL2Z. Yeah. Now one can complete this Eigenstein series and this Dedekind zeta function. And so completed Eigenstein series is defined as lambda 2s times EZS, where lambda 2s is this factor of gamma as pi to the power minus s zeta of 2s. And this Dedekind zeta function can be completed Dedekind zeta function is defined as 2 pi to the power minus s, then discriminant absolute value of the discriminant to the power s by 2 gamma s, then Dedekind zeta function. So therefore, if one completes, then we have a very nice identity, namely this completed Dedekind zeta function can be explained or can be described in terms of certain average value of this modular object E star ZAS evaluated at certain CM point. Yeah. So this is a very nice identity, and we will be actually exploring this identity to study these connections between modular forms of modular functions on the complex upper half plane and modular functions on three-dimensional hyperbolic space. So let me just start. So this completed Eigenstein series, the analytic properties of completed Eigenstein series, if one uses, then one can in fact prove the analytic properties of this completed Dedekind zeta function. And so the analytic properties of completed Eigenstein series is known, and so it is entire except at the points 0 and 1, and it has a simple pole with residue half, and it satisfies a functional equation. And if one uses this, one can deduce the analytic properties of the completed Dedekind zeta function. Moreover, both sides has a residue, both sides have a pole, and therefore if one compares the residues on both sides, one can get a Dirichlet class number formula for this imaginary corresponding to this imaginary quadratic field, namely is the Dirichlet L function at the point 1 is encodes all the invariants attached to the imaginary quadratic field, namely class group, roots of unity, discriminant, and all. Yeah. And so these are just very applications of this identity. And the third applications that will be of interest of today's talk is that in this case also, we know that this Dedekind zeta function factors as Riemann zeta function times Ls chi d. And Goldfeld and Hofstein proved that this zeta s times Ls chi d, in fact, this zeta s turns out to be the first Fourier coefficient of Eigenstein series of weight half for the congruent subgroup gamma naught 4, and Ls chi d turns out to be the dth Fourier coefficient of Eigenstein series of weight half for gamma naught 4. So therefore, on the one side, we are getting the product of first and dth Fourier coefficient of certain different type of Eigenstein series, which is weight half for the level gamma naught 4. And on the other side, we are able to get Eigenstein series of weight 0 for the full modular group. So therefore, somehow weight 0 here is somehow related to weight half, and level 1 on the right side is somehow related to the level gamma naught 4. Yeah. So motivated by this identity, one would like to ask that whether such a relation holds for. So also note that these Eigenstein series are non-Cusp forms, and so for the non-Cusp forms, we have this nice identity which somehow connects this weight 0 to weight half, and level 1 goes to level gamma naught 4, and this gamma naught 4 is the natural very first congruent subgroup that one can talk corresponding to the level 1 on the right hand side. So therefore, there is a connection between weight 0 and weight half Eigenstein series, and one would like to ask whether similar identity holds for general Cusp forms as well. Yeah. And so there is so let me just define what do we mean by Cusp form or mass Cusp form. That I think I've already defined in the morning lecture, so I will be quick a bit. So a mass form for the full modular group SL2Z with complex parameter is in fact a smooth function from the complex upper half plane to C, which is invariant under the action of SL2Z, and it is an eigenfunction for this hyperbolic Laplacian, and this function should be a polynomial growth at the cusp I infinity. Yeah, and as usual, one can see that these such forms have Fourier expansion, and one can similar way say that it is a Hecke-Mascus form if f is an eigenfunction of all the Hecke operators, and the constant term should be 0 for the cusp form here. So that is the definition that we have here written. And this function is an even function if you take the very first negative Fourier coefficient that has to be equal to 1. Yeah? So this is just definition. And similarly, one can also define mass form corresponding to the weight half for the congruent subgroup gamma naught 4 with parameter lambda. Here f of gamma z will be some automorphy factor times f of z, and the automorphy factor will be corresponding to the weight half, and it should be an eigenfunction for the hyperbolic Laplacian, and here the Laplacian corresponding to the weight half here, and so here so it will be minus 1 over 2 iy del over del x. So extra term will be corresponding to delta half, and then f should be a polynomial growth at each cusp of gamma naught 4. Yeah. So similar way one can define mass cusp form and Hecke-Mass cusp form for weight half, and then the beautiful result of Katok and Sarnak in fact answers the question that if one gives Hecke-Mass cusp form of weight 0 for SL2Z, which is even, then there do exist non-zero weight half Hecke-Mass cusp forms for the congruent subgroup gamma naught 4, such that the if one sees the product of first and dear Fourier coefficient of this weight half is in fact can be written or can be understood in terms of certain average value evaluated at the CM points. Yeah, and where phi is your Hecke-Mass cusp form for SL2. Yeah. So this is the result that Katok and Sarnak have proved, and this is one of the nice results. And somehow, if one compares the Fourier coefficients corresponding to weight 0 and weight half, the formula for the Fourier coefficients somehow fits corresponding to the Shimura lift for the case of holomorphic case of modular forms of weight k and weight k plus r. Yeah. So motivated. So what just we would like to point out that the writing Dedekind zeta function in two ways, namely one side if one writes as a sum, on the other side if one writes as the product, the sum and product are sort of responsible to predict correspondences on the automorphic side. And motivated by this, the result of Katok and Sarnak, Mizuno introduced three-dimensional analog of Katok-Sarnak type correspondence. So this correspondence is given in terms of Poincare series. So let me just introduce this. H3 is the three-dimensional hyperbolic space, which is the points Z plus Rj. So here Z is a complex number and R is a positive or real number. And here, so this S3 sits inside the quaternions and real quaternions, and here ijk, if one writes in terms of ijk, then they satisfy the cycle relation, and I square is equal to j square is equal to k square, which is equal to -1. So this is a three-dimensional hyperbolic space, and one defines an automorphic function for this SL2O. Here O is the ring of integers, and then one defines an automorphic function is a function from three-dimensional hyperbolic space to complex numbers, which is invariant under the action of SL2O. And so let me just say that SL2O acts on this three-dimensional hyperbolic space. And so one is demanding that this function should be invariant under the action of SL2O. And this function should be at least twice differentiable with respect to the variables x, y, and r. And so it should be also an eigenfunction for Laplacian. So here in the case of three-dimensional hyperbolic space, so Laplacian is given in terms of this. And so this automorphic function should be an eigenfunction for this Laplacian. And then with this definition, Mizuno defines in a log of CM points corresponding to the complex upper half plane in the case of three-dimensional hyperbolic space. And so what he defines that if you give me a binary Hermitian form T, which is A, B, B bar D, where B is in inverse different and A, D are integers, we satisfy this condition. Then if you give me a binary Hermitian form of this form, then one can associate a point in the three-dimensional hyperbolic space just as B by D plus the square root of determinant of this binary Hermitian form, determinant of T by D times J. And so he defines, if you take an automorphic function, then he defines mth trace of this automorphic function as summation over all this binary Hermitian form modulo the action of SL2O. Let me just say that SL2O acts on this L2 plus M, and this action is given as T goes to UT like this. And here this, and one can, in fact, it turns out that this L2 plus M modulo gamma is in fact finite set, and this sum runs over in fact a finite set. Then f of pt over epsilon of t, where epsilon of t is the cardinality of this stabilizer group under the action of this SL2O. And so Mizuno defined this in a log of average value of CM points in the complex upper half plane that we saw in this three-dimensional hyperbolic space in this way. And then he constructed a certain type of Poincare series, which is known as Niebuhr-Poincare series, and which is again defined explicitly in terms of SL2O modulo the translations here. And this R of AP is the real part of this, what to say, AP, where A is a SL2O matrix acting on the point P. And this is certain modified Bessel function, I2S minus 1. And then e to the power trace of nu. Here nu is, so this Poincare series is defined corresponding to each element of the inverse different. And this nu corresponds to this nu here. And trace of nu ZAP, and trace here means that this is defined. So if you think of it as a complex number, then trace of Z is nothing but Z plus Z bar. Yeah, where Z bar is the usual complex conjugation. Yeah, so, and he also constructed a suitable Niebuhr-Poincare series on the complex upper half plane of weight k, and for the label gamma naught d. Here d is the discriminant of the imaginary quadratic field, and he so corresponding to the each divisor of this discriminant, he constructed this Poincare series, and somehow these divisors are somehow related with the corresponding cusps of gamma 0 d. So in the case of when this D is square free, then there is one-to-one correspondence between the positive divisors of D and the cusps. So this D1 corresponds to the Poincare series at that cusp, and he defines suitable Poincare series on the complex upper half plane of this type. Yeah, and then what he shows that if you take a square free integer, which is negative integer, which is the discriminant of an imaginary quadratic field. And then he shows that if you take the Niebuhr-Poincare series for the level gamma naught d, then this Niebuhr-Poincare series, then the Fourier coefficient of Niebuhr-Poincare series can be expressed in terms of the mth trace of this nth Poincare series for the three-dimensional hyperbolic space. And here, as you see that f nu is in fact automorphic function for SL2O. Yeah, so here is the gamma is SL2O. One can in fact prove that this is an automorphic function for SL2O. So here, what he proved that this Fourier coefficient of Niebuhr-Poincare series on the complex upper half plane for the label gamma naught d somehow related with the Niebuhr-Poincare series on three-dimensional hyperbolic space corresponding to the label 1. Yeah, so he somehow proved that label D corresponds to the label 1 in three-dimensional hyperbolic space corresponding to the Bianchi modulo 2. Yeah, if you take gamma naught D as a congruent subgroup of SL2Z, then this somehow corresponds to the label 1 inside the Bianchi modulo 2. And this Poincare series is defined on three-dimensional hyperbolic space. And so this is a sort of result that Mizuno proved. And so then one is interested. So if one remembers that somehow this gamma naught d, if one remembers this this Doi-Naganuma lifting, so here, so let me just recall that this here d with character chi d somehow goes to label 1 in the Hilbert-Modler form side, and Mizuno's result somehow reflects on this theme that label d Niebuhr Poincare series is somehow related with the label 1 Niebuhr Poincare series inside the three-dimensional hyperbolic space. And therefore, similarly, one would like to understand what happens the label 1, if you take label 1 form, label 1 Niebuhr Poincare series on the complex upper half plane, whether that can be lifted to, whether that can be connected to certain Niebuhr Poincare series on three-dimensional hyperbolic space for the label 1 Bianchi-Modler group. Yeah. So this is the question, and in order to answer that question, we introduced a twisted analog of above trace. So we have introduced the twisted analog of this trace, which is defined as if you this psi d, and this psi d is essentially Dirichlet character corresponding to corresponding to the imaginary quadratic field. And so one defines the mth trace of this function corresponding to this imaginary quadratic field D and general label M. And instead of L2 plus M, one need to here, as one has taken that L2 plus M, and instead of this, one need to take here L2 plus MD square, and one need to go modulo gamma naught NO, and one can define the twisted mth trace. And here psi d of t is essentially this, what to say, this psi d of t is essentially this Kronecker symbol, because if you have given this binary Hermitian form, this then psi d of t is essentially d by a, or chi d of a. One can define Kronecker symbol chi d of a. Yeah, so one defines this twisted trace, and then one what proves that if you give me, for example, here level 1 or level n form Niebuhr Poincare series on the complex over half plane with respect to the congruent subgroup gamma naught n, then this level n Niebuhr Poincare series can be connected with the mth trace of level n Niebuhr Poincare series on the three-dimensional hyperbolic space. Yeah, so this is, and so therefore label n goes to label n, and this somehow gives a certain connection in the spirit of Doi-Naganuma lifting, that label n goes to label n and label d goes to label d with character chi d goes to label 1. Yeah, so this is the result that we have proven in this direction, connecting modular functions on three-dimensional hyperbolic space and modular functions on the complex upper half plane. And moreover, we also generalize the result of Mizuno to general congruent subgroups. So if you take a Niebuhr Poincare series on the complex upper half plane for the congruent subgroup gamma naught M, and if M is divisible by the D, where D is the discriminant of imaginary quadratic field, then this Poincare series can be related to the label M by D Poincare series, M by D corresponding to the congruent subgroup of Bianchi-Modler group corresponding to gamma naught M by modulus of D, and this Niebuhr Poincare series on three-dimensional hyperbolic space. That means the Fourier coefficient of certain Niebuhr Poincare series can be understood in terms of mth trace of Niebuhr Poincare series on three-dimensional hyperbolic space corresponding to the congruent subgroup gamma naught M by D. Yeah. So this is the result that we have discussed, we have proven, and so let me just give quickly the idea of the proof, and then I would like to stop our lecture. So here, what one does, that idea is to somehow construct suitable Niebuhr type Poincare series corresponding to the various cusps of this gamma naught absolute value of D. And here, since D is square free, D is 1 mod 4, so D is square free, and then one use the benefit of the correspondence between divisors and the cusps of gamma naught D. And then one need to suitably construct neighbor type Poincare series at various cusps, and then one need to form certain linear sum, corresponding linear sum of these neighbor Poincare series. And this is the idea of Z here in the case of diagonal anomal lifting case. And then what one tries to construct then another neighbor type Poincare series corresponding to the three-dimensional hyperbolic space. And then one need to explicitly compute the Fourier coefficients of both these Poincare series. And then if one computes the explicit Fourier coefficients of both these Poincare series, then one need to somehow match the corresponding Poincare series. And this corresponding Poincare series is just matched by looking the individual Fourier coefficients. And in order to match these individual Fourier coefficients, one need to understand this finite exponential sums over imaginary quadratic fields and these Klustermann sums. And therefore, one need to establish a certain identity between finite exponential sum over imaginary quadratic field and this Klustermann sum corresponding to the SL2Z corresponding to the in the case of if one goes modulo integers, then we have Klustermann sums or Sally sums. Yeah. So therefore, one need to establish the identity, and somehow we have proven that explicit identity, and that explicit identity requires, in order to prove that, requires somehow finite Fourier transform, and the identity is relating this Gauss sum and Jacobi sums and all. And using that, we have established this finite, this exponential sums and Klustermann sums, and we have proven certain identity, and those identities were responsible to establish such a connection. Yeah. So this is the basic idea of the proof, and we will not go into the technical things. And so therefore, now I would like to stop here. Thank you very much.
Yeah, thank you very much for the beautiful talk. Are there any questions from the audience?
Yeah, Malik.
Yeah, please.
Yeah. So those two spaces that you considered, like in the level 1 case, so there were two ID maps, the lift map, so that the direct sum is isomorphic, like SKSL2, that SK T ID plus SK SL2G is isomorphic to SKSL2.
No. Actually, they sits inside SK of SL2, and in fact, what is this? That SK, this in fact goes inside the symmetric Hilbert modular form. This direct sum SK of SL2Z, direct sum SK D chi D, they actually somehow exhaust the symmetric Hilbert cusp forms. So this SK of SL2O is a priori a huge space, and this somehow captures the symmetric part of this Hilbert model form. And symmetry, I mean that omega of Z1, Z2 is omega of Z2, Z2. If you have Hilbert model form, F of Z1, Z2 is F of Z2, Z2. So this captures the symmetric Hilbert cusp form.
Thank you. Are there further questions?
Manish, did answer your question?
Yes, it answered, but there are other things also. Look, I will ask you again.
Okay.
I think you can go ahead with asking questions.
I may have to look again myself.
Okay.
Yeah.
Yes. Good. Are there other questions from the audience? It looks like this is not the case. Yeah, then let's thank the speaker again very much for a very
Thank
nice
you.
talk. Okay. And we will resume at 3:10 with the second talk of this afternoon session. Is our second speaker in the audience? Yeah. Hello, yeah.
Hi.
How are you?
Yeah, fine.
Good, good, yes. Maybe you can share your slides already?
Okay, is it visible?
Yes, yes, very good.
Hello, sir.
Yes, hello. Finally, I made it.
Yeah. Okay.
That is really difficult. Again,
You
I
are,
have to shift to many places. Finally, I found a place where I can put my laptop and talk. I am in the guest house, so.
not yet all settled.
What it is of self?
Not yet all settled.
Nothing. Yeah, it takes some more time.
Yeah, maybe 2 more minutes. It's 2 more minutes and then we can start. Yeah, it is time. It's my pleasure to announce the second talk in this afternoon session. Professor Ramakrishnan from the Indian Statistical Institute in Karlsruhe will talk about representations of a natural number by certain quadratic forms.
Okay, thank you for your introduction. And yeah, thanks for the organizers for inviting me for this talk. So I've been traveling, so I've been shifting. So there were a lot of in the midst of my other schedule, I'm not yet settled here. So somehow I managed to keep my talk. So this I gave a talk I think 2 weeks before in the Pune ISF Pune Subara Symposium. So the talk will be 50% from there, and then I added one more theme so that a common theme I wanted to have. So we'll discuss mainly the two problems. The effect, the point is that not on the problem, but as a consequence of getting these results and what are the consequences of these results. Okay, or rather than the method, and then as a consequence we get an interesting result. So that's what I'll focus in this talk. Okay, so we consider the problem of finding formulas for the number of representations of an integer by an integral quadratic form of odd number of variables, especially the diagonal forms. So our method is to use the theory of modular forms, especially the Shimura correspondence between modular forms of half integral weight and integral weight. So in this talk, we shall discuss about our results in this direction and focus mainly on the consequences of our method. The consequences led to some interesting results in the theory of modular forms of half integral weight. So though it is known that one can use this modular form half integral weight theory to get the formulas, and then the main point is that though the result is not so difficult to get it, but as a consequence, we get interesting consequences. That's what I will concentrate. Okay, so I'll be talking about only the the odd number of variables, and even in the history part, I'll briefly indicate that what are the things known in the case of when the even number of variables. So notation is that Rkn is the number of ways a natural number n is written as a sum of k squares. So take the cardinality of x1, x2, xk, such that n is written as x1 square plus x2 square plus k square. K is any integer. So number of ways of a natural number written as sum of k square. The study has a very long history, and initially then when k is even, for the value is 2, 4, 6, 8, Jacobi gave a formula, and then he uses elliptic functions to get it. For more general k even, Ramanujan gave a formula, and later it was proved by model. So what Ramanujan did in his famous work, again 1916 paper, so he expressed this Rkn when k is even explicitly in terms of the divisor functions coming from the Eigenstein series part, and also he estimated the error term coming from the Fourier coefficients of cusp forms. Therefore, when you write this Rkn in the generating, I'll mention what is the generating function. The generative function is a modular form. So therefore, the modular form can be given in terms of the Eigenstein series plus cusp form. The error term comes from the cusp form, and then he found explicitly the Eigenstein series part, and then in that paper he gives that, and then he gives a very nice error term he gives, okay, there. And then why he has taken this particular work in that paper is, this was done in connection with his conjecture on the Fourier coefficients of the delta function, which is the Ramanujan tau function. He gave an estimate, that is the conjecture of Ramanujan. Later it was generalized by, the conjecture was Ramanujan-Peterson conjecture. It was solved by Delhi. So in this connection, he considered this one kind of finding formulas for Rkn. And then for k equal to 12, he gave a formula for this one involving the tau function. So there are several works in this direction. If anybody wants to see that, they can refer to the papers of Cooper, Milne, Ono, Imamoglu, Conan, etc. So they all give about the how to find the formula. Give a formula involving very nice functions. So Rkn when k is even. So when k is odd, formulas are not known for more general. So for values of 1, 3, 5, 7, 9, 11, 13, one knows these kind of works in terms of the works of Hurwitz, Sandam, Van Asch, Lomardze, Barakun, Hirschhorn, and Cooper, and many more others. Okay, and unlike the case of integral k is integer, for the k even, when k odd, formulas for Rkn is not known in more general. Only Rk of n square is known when k is odd. So that's what we'll see. Still Rkn for only for small values of k odd are known, but not in more general. So in his work, Van Asch extended the Shimura correspondence, which I will describe in a moment, and suggested that the extended lifting can be used to get formulas for R2k plus n square, but it was not available until we did the work. So in our earlier work, Savoli Gun, my former student, this work was done in 2005, published in 2008, took a long time for publication. We used the Shimura correspondence to give a general formula for R2k plus 1 n square. So the focus is not on the general formula, but as a consequence. So brief sketch of the result which we have already done. The space is denoted by mk plus of 4 and chi, C vector space of modular forms of weight k plus of on the group gamma 0 4 n with character chi. This mk and chi is again vector space of modular forms of weight k on gamma 0 n with character chi. So for cusp forms, we use a symbol S instead of capital M. They are subspaces of cusp forms. So what is the Shimura correspondence? Briefly, that if f is AFN is the coefficient of f, Fourier coefficient is a cusp form of weight k plus half, level 4 and character chi, where this variable q is e power 2 pi I z. Then for a square free integer with t with minus 1 power k t positive, t is missing. The t Shimura map is defined by st of f is given by this particular formal sum, that summation over all n, the d dividing n, minus 1 power k t by d, chi of d power k minus 1, af of mod t n square d square by d square to q power. So this condition d comma 2n is 1 is not needed when you can put the character here, because chi is a character modulo 4n. If chi is a trivial character, we have to put this condition. So it is a fact that St of f belongs to integral weight modular form s to k of level 2n and chi square. Okay, so extension of Shimura maps, because we need this extension because the cusp form is not sufficient for us. We need to extend the map defined by Shimura to non-cusp forms. So in 83, Van Asch did it for gamma 04, extended the map to non-cusp forms. In 2003, Wang and Pai extended the Shimura-Conan map to forms which are the maps defined on the subspace of the mass space of cusp forms defined by Conan, which is called the plus space. So for that, restricted to the plus space, we have a map defined by Conan, which is Shimura-Conan map. So what they did is they extended the Shimura-Conan map to the Conan plus space for gamma 04n, where n is odd and square free. So this work I will explain now. This is 2010 with Monicam and Savoligun. So we observed that one can deduce the mapping property of the Shimura map from the result of Wang and Pai. So when n is odd and square free. Therefore, extension of Shimura map for this case can be done when n is odd and square free. However, these works are not sufficient if you want to use this method to get this kind of formula in general, for which I think we make use of result obtained by Monicam with his co-authors, which extending these results to more general n. So t is a square free integer with the minus 1 power kt positive, and d is either t or 4t depending on t1 or 2 or 3 mod 4. So d is a fundamental discriminant with minus 1 kt positive. Then for a modular form f with coefficient a of n, weight k plus of level 4 and character chi, then the dth Shimura map and the dth Shimura-Conan map are defined as follows. So the difference is only the non-constant term. So when you look at this n greater than or equal to 1, the term is exactly the same. Only for the constant term has to be defined. That is, a of 0 is the constant term in the Fourier expansion. This hkt, which I will describe below. So the other things are the same as before. And then for the Shimura-Conan map, a0 of h of d in this one. So where hk of t is the Dirichlet L function, L at 1 minus k, special value at 1 minus k of the character d by dot, and some the product, this factor will be the some constant. For hk d is the difference between these two is only the prime 2 will be appearing here and p2 will not appear in this d. So these are the definition. Then when k is greater than or equal to 2, then STF is in m2k of 2n when n is odd, and if n is even, one has to apply the Shimura-Conan map. So that is the result of Monicam and Jagadish. Okay, we make use of this. So the generating function for the sums of squares, I see for the this part of work, I am not going to use the more general one. So I am talking about this one. For this one, we just make use of Van Asch result, which n can equal to 1. So when I talk about the second part of the result, I think we need that's why I put it in the beginning itself. Okay. So the generating function for the sums of squares is the classical theta function, which is the theta z is e power 2 pi n square z, n runs over all integers, which is a modular form of weight half and level 4. Therefore, we have, if I take the 2k plus 1 power of this theta series, the coefficients will be the r2k plus 1 n. So it is a modular form of weight k plus half on level 4. Therefore, in order to find the coefficients r2k plus 1 n, which is the representation number, we have to study this function theta power 2k plus 1 of z. So this is the modular form of half integral weight. Therefore, if I apply the Shimura map on that, this one is mapped to the integral weight m2k of 2. If I apply the s plus minus 1, then we have the r2k plus 1 n square by d square coefficient appearing in this side, and which is a modular form of weight 2k and level 2. So if I find a basis for this particular space and then express the whole thing in terms of a basis on the right hand side, and then comparing the nth Fourier coefficients and taking the Mobius inversion, then finally we obtain r2k plus 1 n square. That is a method which is a simple way you can use one. So writing the right hand side as a linear combination of basis elements, the main part is to find a basis for m2k2 for general k and compare the nth Fourier coefficients in the above equation, and then using Mobius inversion, you get R2k plus 1 n square as this kind of sum. So this the M2k is spanned by the Eigenstein series of weight 2k and its duplication and a cusp form. So that's what I'm writing this as this Eigenstein series E2k coefficient, is E2k of 2z coefficient and a cusp form. And then for the cusp form also we have an explicit basis. So for writing simplicity, I put it as A of n by d. Otherwise, whatever the dimension, so many parts will be there in this expansion also. So the an are the Fourier coefficients of a cusp form. So for simplicity, I made it, but one can write more explicitly the basis for S2K2 also. In terms of the basis coefficients, it will be appearing. Okay, so what is the big thing about this particular formula? So when you do this explicit one, when you put values of k, for example, when I put k equal to 10, so it will become R21 n square. So when I do this space M2k n equal to 10, M20 of 2. So when you have the M20 of 2 is spanned by this Eigenstein series E20 of z, E20 of 2z and 4 cusp forms. Okay, so but when you do this explicit computation, only the coefficient corresponding to E20z coming here and then corresponding to 3 cusp forms appear here. So somehow the E20 of 2z and 1 cusp form dropped out in the formula. But not only this one, but in few more cases, similar vanishing of the terms on the right hand side happened. So we didn't know why it is happening. So when Savonli visited Norway for a conference, I think she showed it to Dan Zagier. So what, after looking at these examples, explicit examples, he did some kind of calculation and then told that whenever k is 2 mod 4, he made this observation that the image of theta for 2k plus 1 under the Shimura map lies inside the space M2k1 rather than M2k2. It should lie in M2k1. That's what he says. So whenever for certain values of k, if I apply the Shimura map, it should not be in M2k2, but rather than it will be in M2k1. So that's why it is happening. So this is his observation. And not only that, this is the main reason for this particular thing is due to some property of the eigenspace under the Atkin-Ladder W operator. That's what he told, but he didn't elaborate, it seems. Then with joint work with the Savonli and Manikam, we could do the characterization, and as a consequence, we could prove this result. So that is one of the surprising application when you find this formula for R2k plus 1 n square. So that is the one instance. I'll explain the results we obtained in the paper appeared in 2010. So n is an odd square free integer. W4 is the Atkin-Ladder W operator corresponding to the prime 2. So these are all analogous W operator in the case of half integral weight. So this was done already in the case of integral weight while studying the theory of new forms introduced by Atkin and Ladder. So similar things was introduced in the case of half integral weight, and that is a W operator. And then the W operator is an involution, so it has eigenvalue plus minus 1. Therefore, it is natural to study the plus minus eigenspaces of W4 operator. You take the plus minus eigenspaces corresponding to the prime 2. That's why this plus minus comma 2 is there. Collect all the forms such that f of W4 is plus minus f. Then one can characterize the space in terms of the Fourier coefficients. The characterization is done if I intersect this with the new form space. When n is odd and square free, there is no new form in the case of the non-cusp form, and therefore that Eigenstein series part. Therefore, we need to intersect this with the new form. Therefore, we have the cusp form sk plus of plus minus 2 intersect with the new forms 4n. If I consider that particular intersection with the new forms, then it has a nice characterization that it contains all new forms such that the nth coefficient is 0 whenever minus 1 power k n by 2, the symbol value is minus or plus epsilon k, where epsilon k is 2 by 2k plus 1, this is the Kronecker symbol. So epsilon k is also plus minus 1 depending on the parity of k. So when the right hand side becomes minus or plus 1, so it belongs to the plus minus 2 space. So this is the first characterization which we proved. As a consequence, we obtain the following theorem. So when t is 1 mod 4, the square free integer such that minus 1 power k t positive, and take t relatively prime to capital N, and t by 2 is minus plus k. So that epsilon k. So that you have same thing you have to assume. Then the t Shimura map takes the plus minus 2 eigenspace of half integral weight into M2K M. Generally, the ST map maps in K plus of level 4n to level 2n, but here because of this special property, we have the ST is mapping down to the level capital N. So in particular, when you apply when capital N equal to 1 and T by 2 is minus epsilon equal to 1 and T by 2 is minus, I have to take the minus epsilon K. So therefore, the ST of theta for 2K plus 1 is in M2K. So therefore, we can get a consequence for certain whatever the values of K with satisfying this property. Then with this property, then I can apply ST and then write this in terms of the basis for M2K of 1 and find a nice formula. So this is the theorem, and once I use this one, we can get very nice also congruences we get using this. Using the above theorem, we get a formula for R2K plus 1 n square in a simplified form, which involves the Fourier coefficients of basis elements of M2K1. So we also obtain certain interesting congruences in this direction. You take the R13P square plus P is congruent to the Ramanujan tau function modulo 5. R21P square plus 2P congruent to 2P into tau of P mod 5. Also for modulo 7 also we have a congruence this. So for this, in most of the things you will have one congruence like this, and then some cases we have two congruences. So where tau n is a Ramanujan tau function. So this is one of the interesting applications which we have obtained as a consequence of doing this problem of finding the formula. Now I move on to the other problem, which I already did in the Subarov symposium, but I'll little bit more I added now. The next work which we will discuss is an ongoing work with Vrindavan Sahu and Anup Kumar Singh. This work is also about formulas for the number of representations, but for the forms of the type with coefficients. We studied with the earlier cases x1 square plus xk square. Now I can add coefficients. Here we are not writing in more general because the problem becomes more difficult because the level also will explode. We do not know, we don't have control of this one level. When you put k equal to 5 and 7 and then restrict the coefficients, then we can somehow do that. So these are diagonal forms, sums of squares with the coefficients, and are referred to in the literature as the quinary and septenary forms. So we took up this problem, which extends the works of Cooper, Lamb, and Yee, who have done this work when k equal to 5 and 7 for certain coefficients, and they appeared in the Arithmetica and Integers in the same year 2000. There are two papers. First paper appears with k equal to 5, and then the integers paper with k equal to 7. The method in both the papers are the same, which we'll describe in this now. So their result also, method also we just mention now, which is called the Hurwitz method. So more than 100 years ago, Hurwitz determined the number of ways an integer can be expressed as sum of 5 squares. He proved the following formula. You write n as the prime power factorization, then the cardinality of the set, that R5 of n, this is exactly R5 of n square, is given by 10 times this number times product of p greater than or equal to 3, this factor. So this is for R5 of n square. So there are results for R7 n square and then etc. But there are results by Sandham, R9 also it is done by Cooper. So I'm removing those things results in this particular odd number of variables which you can refer. I gave some references there, names. From there you can see that. And most of them are use this type of Hurwitz method only. So in 2013, in Arithmetica and these three authors obtained analogs of the Hurwitz theorem to find the number of ways n square can be expressed by the following three quinary forms. So one is with coefficient 2 appearing, then coefficient 3 appearing, and 2 and 3 appearing. These three formulas they obtain, and then making use of these three, and then they also obtain another 15 forms and formulas for these forms. So the coefficients in this case, they belong to 1, 2, 3, 4, 6, but not all of them will appear in 1, but therefore in 15 it is distributed. Okay. So these are deduced from the formulas for the 3. So the 15 formulas are obtained with some reductions, and using these formulas, they obtain 15 formulas. So instead of R suffix the number of variables, I put the coefficients below, and the n square denote the number of representatives of n square by this form in 5 variables, aix I square. So the three formulas of Cooper, Lamb, and E are given by this. So with coefficients 1, 1, 1, 1, 2 is the constant for 2 part is 8 when n is odd, Otherwise, this factor when n is even. For p greater than or equal to 3, we have this one. And when coefficient is 3, we have the 2 factor here, 3 factor checked out. What he does is that we just to have a recurrence relation for n as 2 power 2 lambda times the odd number, then you take the 3 part and then you find this number separately, and then for general one can find out. And similarly for this 1, 1, 1, 2, 3 also. So the 2 part is done separately, 3 part is done separately, and then one can do the remaining part. That is because of the character modulo 3 appearing here, therefore the 3 comes out. Here also the 3 part is there, that comes out. 2 part is always comes out here. So we shall briefly describe the key ingredient, how this they make use of what is the Hurwitz idea, and then what is how it is used. So the lemma is a simple lemma. So an is a function which is defined for all non-negative integers, satisfying the following multiplicative property. A of Pn is AP an minus chi p A of n by p for all primes, and chi is a completely multiplicative function. Then here is n by p is 0 when it is not an integer. Therefore, ax is 0 where x is not an integer, with that understanding. So this is non-zero only when p dividing n. So define this capital An by summation an q power n is summation a of k q power k whole square. That is, if I take the Fourier series with the an coefficient, square it, the coefficient is capital A. So z is in the upper half plane, q is e power 2 pi a z. Okay, so then the coefficient of q power n square in the expansion of this is theta function, theta times this Fourier series using the coefficients an. So you consider this Fourier series considering the coefficients an and then multiply by the theta function. And then you have to take the product and take the n squared coefficient of the expansion. It is exactly given by this summation r equal to 1 to infinity a of 2n by r chi of r mu of r. Again, this is a finite sum because it only when r dividing 2n the sum survives, otherwise it is 0. So here mu is the Mobius function. This chi is the function, multiplicative function coming from the multiplicative relation here. So this is a very simple one. One can we'll just see a proof of this one. So as before, theta is the generative function for the squares. It is a weight half modular form, and this is fundamental in the theory of half integrated form. So the generative function for this form is exactly the product of theta with the coefficient ai. So theta of ai is that you take the product, and this is the generative function for this particular quadratic form. So which is a modular form of weight pi by 2 for some congruent subgroup 4 of n, where n depends on the coefficients ai. So now this is a modular form of half integral weight, how they apply the result. Okay. So for that we need to have at least one of the coefficients will be 1. So therefore you separate one theta and consider the other 4 theta series. You take the product and then write them as functions f1, f2, fm, such that the f is the product of the 4 theta functions, the remaining theta functions, and then this f if we write as f1, f2, fm, such that each fi has the Fourier coefficients ajm which satisfy the properties in the lemma. So whatever the lemma and property I mentioned, so the fi should have the coefficients satisfying this one. If you write the f as a sum of these forms with this property, then you can apply that. Otherwise, you cannot do that. So therefore, assume that your function f is written as a finite number of forms having the coefficients with the multiplicative property as in the lemma. Therefore, your original function theta f is nothing but the summation theta of fj of z. So f is the sum of fj. Therefore, theta f is summation theta fj. So for each theta fj is given in terms of this aj of 2n by r chi j of r mu of r by the method of Hurwitz. Therefore, summation j theta of fj is given in terms of I have to sum over all this j. So this is the way they find the formula, and then you do the simplification and put it in this nice form. So this is very elegant method and it works only in the case of certain cases. The difficult part is to write f as the even number of theta functions as the sum of functions whose coefficients satisfy the multiplicative property. Okay, so in another work, same authors and then extended this method for 7 variables with coefficients 1, 2, 4. So the coefficients are chosen in such a way that the combination of the even number of theta functions can be written as a sum of function modular forms with multiplicative Fourier coefficients. That is the whole key idea in all the results. So then they prove that with the coefficients 1 power 6 comma 2 and then 1 2 power 6 takes a very nice form. And what did I write? Yeah, this is nothing more. I think the result is exactly the same. For 7 also you write theta into f. F is the product of 6 theta functions. Again, the product of 6 theta functions write as a sum of cusp forms with coefficients multiplicative, and then apply the method and then sum. There is a very complicated method. So therefore, the paper, if you want to read it, it has contains several portions. In each one proves one result, and then finally you combine everything, you get a result like this, and then you get your final formula. So the first one, we consider the form sum of squares and then obtained a formula, and then the characterization was done as a consequence to that. In our present work, in the joint with Brindavan and Anu, we obtained a generalization of the result of Cooper Lamb E with sum of 5 and 7 squares. We extend the coefficients which belong to a larger set. So here again, we make use of the Shimura correspondence, and then we talk about the consequence of using this type of method. So I'll just mention only one idea of result, and then we'll go to the, as a consequence, how we get it. Okay. So take L equal to 5 or 7, A1 x1 square, A2 x2 square, AL xl square, then RAL of, this is the notation. Okay, you can just forget because there's a number of representation of N as the sum of A1 x1 square, AL xl square, the L I put it here, coefficients I put A in the vector. So that is only a notation, that is not a problem. So when all the coefficients are 1, that is exactly RL of N. So if L equal to 5, it is R5 of N. If it is sum of 5 squares, if it is sum of 7 squares, it is R7 of N. So when A equal to 1, 2, 3, they have proved 18 formulas where this coefficients belong to 1, 2, 3, and then for 7, again 18 formulas, the coefficients belong to 1, 2, 4. And then using, there are more formulas in this case, they have 1, 2, 3, 4, 6 also they have done. But basically these 18 formulas are prominent in this. So in our case, we consider more coefficients. These are the cases you can see 1, 2, 3, 4, 11 appears. And the level also increases once you put the coefficients. Depending on the coefficient, the level also varies. Okay, so this is only a few cases when L equal to 5. There are, if you look at the next one, L equal to 5, you consider the levels as 2, 3, 4, 6, 7, 8, 12, 14, 16, 24. Therefore, the coefficients are, when you fix a level, the coefficients are divisors of these numbers. Therefore, and then if you count the number of cases we considered, it will be 417 formulas, which include the formulas obtained by Cooper, Lamb, and E. In the case of 7 variables, we consider the N as 2, 3, 4, 6, and A as divisors of these numbers. And in this case, we have 1 to 26 formulas. So one sample case we demonstrate, and the remaining case is similar. So take this same case of Cooper's result, 1, 1, 1, 1, 2. There is a 5 variable with 4, 1 coefficient and 1, 2 coefficient. The generating function is theta power 4 into theta of 2 z, which is weight 5 by 2, level 8, 2 by dot character form. So under the Shimura map, this is mapped to M2 of 4. And this M2 of 4 is spanned by E4, E4 of 2z, E4 of 4z. There is no cusp form in this case. Therefore, use the first Shimura map, T equal to 1. We have S1 of theta power 4 into theta of 2z. I'm just writing in terms of that one because this is, this is the function theta power 4 of z, theta of 2z is the generating function. The image is exactly 1 by 30 E4 of z minus 8 by 15 E4 of 4z. So the comparing the fourth coefficient, you apply the Shimura map on this definition and compare the nth coefficients, and then what we get is summation d dividing n, d odd is 2 by d, d r5 of 1 power 4 comma 2, n by d square is 8 times sigma 3 minus 120 times sigma 3 of n by 4. These are the coefficients of this Eigenstein series E4. And then taking the Mobius inversion, we have R5 of 1 power 4 2 comma n square is exactly this. So since these are all multiplicative functions, one can also use n as a product of prime power. One can make it the same formula appears in our case also. Therefore, whatever way we approach, they use the Fourier method and we use the Shimura method. The formula remains the same. And therefore, the indication is that there must be some similarity between Hurwitz's method and the Shimura map. That's what we realized, and it is fact, it is true. So the first method relies on expressing Fz as a linear combination of functions having multiplicative Fourier coefficients. Our method relies on finding a suitable basis for the space of modular functions of weight 2 or 3 with a given level. So both their difficulty level are equal. So generalizing these two are not so easy. So only when you can find a basis, we can use our method. Similarly, if you can express this product of even number of theta series as a linear combination of forms with multiplicative Fourier coefficient, then you can use Hurwitz's method. So because that there is no general way of predicting whether it is possible or not. But on the other hand, one can find a basis, but explicit basis is another question. So far I have not seen a paper where it gives a basis for any general n, weight 2k, general level character chi. I have not seen a paper in this. So we make some observation about similarities in both these methods, which is one is the Hurwitz method, adopted by Cooper et al. And the Shimura maps. So again, there is one paper which I also did. I'll talk about that. I'll mention about that, which is with Manish. This talking about this Selberg's idea that there is also a generalization of this kind of method, which is described now. I'll describe at the last slide I do. In an unpublished work, Selberg made the following observation about the Shimura map. So take a normalized Hecke eigenform and consider the function capital F as f of 4z into theta z. And it is a modular form of weight k plus of or gamma 04. So what he observed is that image of capital F under the S1 is exactly f squared times minus f2 power k minus 1 f square of 2z. So that is S1 of f is f square minus 2 power k minus 1 f square of 2z. To prove this observation, he used the multiplicative property of the Fourier coefficients of f and an inversion formula. So similarity is there. You can also, Hurwitz also uses the multiplicative property of the coefficients of f. So here we assume that f is a Hecke eigenform. In Hurwitz at that time, this kind of theory was not available. Therefore, he makes assumption that an satisfies certain multiplicative relation without knowing that it is a kind of eigenform under some operator. So in both the methods, the coefficients of q power n square involves Fourier coefficients of f square of z. That's what both the things. There also it is, if you look at it, that capital A comes here. Let me see. Yeah. So this capital A is exactly the f square coefficient, right? So this capital A is involved in the final formula. In the Shimura map also, that Selberg's also the f square is involved, f square and its sum duplication. So now we use Selberg's method and then we'll just give a proof of Hurwitz, whatever proof lemma he proved, it will be easily proved. So take f a Hecke eigenform, which means that the Fourier coefficients satisfy the multiplicative property mentioned in the lemma, and consider f into theta of z, which is b of n q power n, and then you write bn as a of n minus m square, where m runs over integers. Then b of n square is summation a of n square minus m square. Then you factorize this a of n minus m into n plus m, make the change of variable and do simplification. Finally, you get b of n square as summation over L, a of L into 2n minus L. Now you make use of the multiplicative relation and take the inversion. An satisfies this relation. So in Hurwitz's lemma, these two together is chi d. Okay, so the d power k minus 1 will not appear in Hurwitz's one. Since we are using the modular form theory, the d power k minus 1 comes. Otherwise, it is chi of d, a of nm by d square, chi completely multiplicative. So now use the inversion formula. A of nm is mu d, chi of d, a of n by d, a of n by d. Therefore, using this inversion formula, the previous page, and we have b of n square is a of L into 2n minus L is there. Apply that, then it will become summation over m, d dividing m comma 2n minus m, mu of d, chi of d, d power k minus 1, a of n by d, a of 2n minus m by d. Since d divides m and 2n minus m, d divides m and 2d dividing 2n, so we replace m by md, and then again more simplification you can do. B of n square is d dividing 2n, mu of d, chi of d, d power k minus 1. This particular combination comes. Now if you look at the f square, this is the coefficient of f square is an. So an is exactly a of m, a of n minus m. Therefore, this coefficient is exactly a of 2n by d. Therefore, this you can write as B of n square is summation mu d chi of d d power k minus 1 a of 2n by d. So this is exactly the formula of n square to coefficient as stated in the lemma. Okay, where only chi of d appears there won't be d dividing 2n. It was written by 2n by d varies over integers. So this is the proof of the lemma. Just I'm following the proof of Selberg. Now we assume certain condition and get a mapping property from the lemma. So just if we assume further condition that chi of d is 0 whenever d is even, so the d even part goes away, therefore d dividing n only will be there. Okay, so that we'll make use of that. So assume that chi of d is 0 whenever d is even, therefore the above formula I can write it as summation n greater than or equal to 0 d dividing n dr chi of d d power k minus 1 b of n square by d square is summation a of 2n q power n. So I can just again use the Mobius inversion. This whole thing will go to the left hand side, and the right hand side we have the series of a of 2n q power n as a Fourier series. Therefore, this is again like a correspondence, we get it. And so if your assumptions are valid when capital N is even, so therefore wherever Hurwitz's method is used, this is exactly the case. So the level of the modular form f is exactly even, then chi of d is 0. So therefore the left hand side is nothing but the first Shimura image of f of theta z, and right hand side is nothing but f square. I apply the u2 operator on the right hand. u2 is the Hecke operator for the prime 2. So right hand side is nothing but f square bar u2, left hand side is nothing but the Shimura map of theta, f of theta. Therefore, what is Hurwitz's method is exactly giving this map S1 of theta, f theta z is f square of bar u2. But when you look at the Shimura and Selberg method, it is talking about the image of S1 of the function f of 4z into theta z, which is in terms of f square minus f square bar b2, where b2 is the duplicating operator, z going to 2z. So there is a small, there is very interesting fact that without knowing the theory of modular forms of half integral, right? So Hurwitz made this kind of observation long ago, and it turns out that this is also a correspondence in some sense. Okay, when you assume that some properly, if you look at the level and then assume that n is even, then it fits into the Shimura correspondence. Okay, and two more slides are there. The observation made by Selberg was when n equal to 1. This is what I am talking about with my work with Manish. So n equal to 1. This was later generalized by Shimura for twisted theta functions. So this what Selberg did it for f of 4z into theta. This theta, if you extend it to generalized theta functions, that was done by Shimura. That also conductor is a prime power. So that's what the result of Shimura 89. And then later this is more generalized, done by Hans and Naqvi, that appeared in Ramanujan journal. This is I think around 2008 or something. For this for more general theta functions. All these works talk about the property of the Shimura 1 map on these class of functions, where the theta is replaced by a generalized theta function, where f is a Hecke eigenform of level n. Okay, and they also put a character here because we are taking about a trivial character, but one can also talk about f modular form of Hecke eigenform of level with character, and then generalize the theta function. In more general class of functions, what is the image? Image similar to this it comes. Okay, that was the result of Hans and Naqvi. And in my work with Manish Pandey, which now appeared, I think the recent volume it is there, 2021. So we thought that why only the special property for level 1 map? So one can do it for any Shimura T map. We generalize these results for the Shimura T map. So exactly the proof follows along the same line. There is no difference. We have to do some appropriate assumptions, then everything goes through. The property is exactly true for every Shimura map, not only the Shimura 1 map. So note that another observation which we saw is that they consider f of 4 is at theta, it is a modular form in the Conan plus space. The Hurwitz method, this function is f into theta, but it need not be in the plus space. But on the other hand, when you consider f of 4 is at theta, it is in the plus space. So therefore, the Selberg's observation can be thought of finding the image of a function, a class of functions in the plus space, what is the image of these functions under the Shimura map. So that's what it says. But if you look at the result of Cohen, which appears in Conan's paper, he also talks about similar one. You take the GKK and the weight K Eigenstein series, you multiply by theta, and then if he applies the Shimura-Conan map, he shows that it is GK squared. So there is a difference here. Selberg applies the Shimura 1 map on this plus space form and shows that it is F square and F square bar B2. But Cohen, in his earlier work, shows that if I apply the Shimura-Conan map S1 plus, it is exactly GK square. So the class of forms in Selberg, Shimura, and all these works discuss about the property of the Shimura map and a class of forms in the plus space. When we apply the Shimura-Conan map on these forms, the image will be only F square without any duplication. So that also I worked it out. I think one has to write it more explicitly. So this is also done. Further, proving the above result on applying a relation between the Shimura map and the Shimura-Conan map, which we obtained in my paper with Savoli and Manikam, one also gets this result of Selberg, Shimura, all the results I can obtain. Once we prove the corresponding result for these class of functions, and then the mapping property, that is exactly the generalization of Cohen's result in this setup, show that under the Shimura-Conan map, it is exactly F square. Using this, and then the relation between Shimura and Shimura-Conan map, one can get back these results. So this also is probable. And the main part is that give a correspondence explicitly. This Hurwitz one more general. So these are the three things which the result, all the works are in progress. I hope to complete in the coming days. Okay, so if you have any questions, I'm happy to answer. Thank you very much.
Yeah, thank you very much for this very interesting talk. Are there questions from the audience?
Well, let me ask, this is Jesse. Are you familiar with the work of K.S. Williams? Because he's done some of these representation formulas. I'm not sure if anything on. You're familiar? What is the difference between his technique and yours?
I think K.S. Williams, so most of the works are using some elementary methods. They do a key lemma and then using some key lemma, then they do. And they also make use of the theta series identities. They prove a lot of Q series identities. And then making use of these identities, they can do that. So the result is more or less same, but somehow their method is, you will not see the modular property in their method. So, but probably more the methods are exactly same. But in some cases, they gave a very elementary form on this one way of proving it. That is possible, but not in more general. So when you increase the number of variables and the coefficients, the elementary nature is, I think it is very difficult to do. So there is a limitation of proving such results. Therefore, they have a lot of papers because they cannot be proved in one go. So whenever they can find a kind of simplification, they write a paper. So that you can see, if you look at the paper of Williams and a lot of co-authors, there are a lot of results with fixed coefficients, and then they get a result. I have seen many of them.
Other techniques besides?
Yeah, there is a, see, when you want to do the number of variables, you take a small block of quadratic form. For example, a form of the type x square plus xy plus y square. So you can find a formula for that, and then you can use these blocks. And then once I find a formula in terms of some divisor function, and I put in blocks, and then you can get convolution sums of the divisor functions. And then if I compute the convolution sums of the divisor function, then also you can get the formula. So they have done this also in many papers. So there is another paper result also is there. When you take the divisor function, you take the convolution sum, which is also done in Ramanujan's paper. That paper appears. So one can evaluate the convolution sums of the divisor functions, which are weight 2 coefficients of the weight 2 modular form. Then also you can find formulas for this type of formula, quadratic forms. So that appears in the works of Williams and his co-authors.
Thank you.
Yeah.
Thank you very much. Are there other questions?
Yeah, it's one question. Can I?
Yes.
Yeah, please.
Yeah. In that Fourier method, we are getting out just the theta z, correct?
Yeah.
Yeah. Since we are interested into the coefficients which are divisors of the label, can't we take out like theta of aiz rather than theta of z, and we can look at the image of theta of aiz and whatever remains that part, because since ai's are divisors of the label, we can take out the ai part.
I think you are missing one part is that why all these things work out. The reason is when you take this f into theta, then you take this form a n minus m square.
Yeah,
Then
yeah,
you can do the simplification when you take the n square coefficient.
yeah.
Instead of theta, if you have a coefficient here, the m square part will not be there. It will be some kind of coefficient will come.
Yes, yeah, exactly.
Then what you should do, you have to put this here also some t. So therefore, I don't know, you have to put the t n square will be there. So the Shimura t map will be there. That's what we have done. What we have done is
Yeah, that's why I was saying, like, because
yeah.
we can
The basic method is this one.
Yeah.
But when you put some coefficient here, then you may have to consider that particular map, Shimura map, for the purpose.
Yeah, exactly. That's what I was thinking, that we can take like that theta, then we can vary one more coefficient, we'll get more freedom.
No, that is true. But I think in that case, you have to apply that t should be square free. So that can
Yes, yeah. Square free condition.
Many variations can be done. That's what I told. No, if we follow our paper, many things can be proved. That's what I mentioned.
Yeah, exactly.
So this contains, I think, many generalizations in all the three directions are possible.
Yes.
So one has to find time to do that. That's what I mentioned. At the end, what I told, all the three will be done.
Yeah, exactly. If we take
all the three directions can be done.
Yeah. Yes. Okay. Yes.
Thank you.
Yeah,
Are there further questions?
There is one in chat, sir.
Yeah, please.
There is one in chat.
What is that?
Yes. Okay, I will read. Moment.
Oh, there is a
Okay, Lalit Vaishya, right? What about we say about this method in case of non-cusp forms? Image of OZ, F4Z under Shimura map S1 when F is non-cusp form.
Let me see. I don't know. What is the whether can I see that? Let me see whether I can see the chat.
The chat? Yeah, so you need to, at the bottom there's
no, because I have to
you need to go on
come
chat.
out.
Yeah, okay. Yeah, then you can stop your
yeah, I'll stop
screen sharing.
Okay, then I can see the chat, right? Yeah.
Yes.
What about we say that the method in case of non-cusp forms? What does it mean? Yeah, we are talking about non-cusp forms only. Image of theta is an effusion if F is non-cusp form.
O is theta function. Yeah.
In fact, I think in Hansen Naqvi they say that F need not be a cusp form. I think it is also true, but I need to see that little bit more on that. Okay, so in the paper of Hansen Naqvi, they don't consider F as a cusp form. They also take a Hecke eigenform only, not necessarily a cusp form. So therefore, it is also true. I think this answers this question. But that one has to see that carefully, that whether in what way the non-cusp form is used there. But if it is a cusp form, the things are very straightforward. Then for a non-cusp form, the calculation one has to be very careful.
Okay, thank you.
Okay, thank you.
Are there other questions? This seems to be not the case. Then let's thank the speaker again for a beautiful talk.
Thank you.
And our last talk will be at 4:20. So we give a 20 minutes break now. Hello. Yeah, I can see your slides.
Oh, yeah.
Yeah, hello.
Hi, can you hear me?
Yes, I can hear you perfectly.
Okay, excellent.
Yeah, could you check if you can move your slides? Sometimes.
Yeah.
Yeah.
Good.
Okay, yeah, great. Yeah, looks very good.
Excellent.
Good. Mhm. So you are at Prague?
Technically, yes, but currently I'm in London, in the UK.
I see.
Okay, so it's just almost 12 here.
I see. How are things in London right now? Everything back to normal?
Well, depends which normal. If it's normal of last spring, then yes, cases going up. But otherwise, it's so there's no restrictions, but people should be cautious, kind of.
I see. Yeah. But all restrictions are lifted now.
Since last Monday, yeah. So it's lifted. So many people got vaccinated at least once. So it's.
Yes.
But I think it's fine. I think more or less everywhere in Europe it's okay-ish.
That sounds good.
But well, nobody knows. I mean, yeah, it is what it is in some sense.
Yeah. But I think this vaccination really helps very much.
No, it definitely helps.
Yeah.
So it's just nobody knows how they're going to deal with those remaining people, meaning the people who get vaccinated.
Yeah. That is...
And so hopefully it's going to be done in some sort of rational way instead of irrational. So it's without forcing people, but
Right. But it's difficult. Yeah.
Oh, definitely. But yeah, otherwise I think it's fine.
Good. Yeah, we are expecting a third wave here.
And excuse me, are you in India?
Yeah, I'm in India. Yes.
Okay.
Yeah. So yeah, vaccination is progressing, but not very fast. And
But is there demand? Do people want to get vaccinated?
Yeah.
Okay, so that's, I mean, it's more or less same in Europe. Everyone wants to get vaccinated, or at least wanted. And everybody who wants to get vaccinated, they got vaccine now. So that's really good in that sense.
Yes.
Yeah, and so we are in the midst of third wave in UK now. And
yeah, I've seen that. But now it looks like the numbers are going down again.
Oh well, so the people don't want to get tested because then they can't travel.
Oh, I see.
Because it's a self-declaration, so you self-test usually, and you declare your results, and there's the app. And so some people say that the recent drop in numbers is to do with people don't want to declare the test results, because then they can't actually enjoy the freedom.
Oh, yeah.
So it's
so it's kind of artificial drop.
It is artificial, but again, so given that so many people are vaccinated, even those who get ill, they have really mild cases of COVID. So So I mean, again, so most of the people are really cautious, and we still wear masks in the public transport, which is really good.
Yeah.
And although most of the government says there are no restrictions, most of the companies tend to have some sort of restrictions just to protect their workers and make it more attractive for customers. So there's, so I mean, people demand some restrictions, even though the government doesn't requires it. So it's kind of good in that sense also.
Yeah, that is sensible.
Yeah, definitely.
And how is it at the university campuses?
So in Czech Republic, it was more or less closed. And I think nobody wants to do any decision for the next term because why would you want to predict what's going to happen? I presume, so we were in more or less distance learning for last semester. And we did most of the exams through Zoom, but we did allow small groups to have exams also in person.
I see.
And I presume the next semester will be hybrid, more or less. But I don't think that anybody can tell now what's going to happen, really.
Right.
So we start in late September, maybe October, sorry. We start, and so then the decision will be made.
Oh, then there's still a lot of time. So
yeah, exactly. For everything. Yeah. I hope for the best, but we kind of plan for the worst. So I mean, preparing everything now for distance learning.
Okay. Yeah, it's here the same, I think. I mean, so in our university, we do everything online at the moment. So maybe by the end of the year, things are more normal.
But can you, for example, if you supervise any student for master's or PhD, can you meet in person or not?
No, we meet online regularly, which is of course not ideal, but it's the only way right now, only reasonable way. Also, they are living, part of them live quite far away. And so there's not a normal train service right now.
Oh, but definitely for those who need to travel to work to universities, probably for them better to do distance learning for now.
Yes.
Safer and more convenient also. So I think that makes sense.
Yes. But we all hope that we can return to normal life.
Oh yeah, yeah. That's a big hope for all of us, I suppose.
Yes.
Hello, Professor Pablo Yatsina. Hello, Professor Bayer. How are you?
Oh, hi. Yeah, I'm fine. How are you?
Pretty good. I'm hanging out in India with the air conditioning. Do you have any suggestions how to stop students from cheating online?
Oh, that's very difficult.
So I mean, so I study. Excuse me. I teach most of the time my master students, so the higher classes, and it's a smaller groups. And so it is optional courses that I teach, and I kind of the opinions that they're usually cheating themselves more than me. So it's I don't really. So I can make harder tests, but in the end of the day, I think. They choose to take my course and they don't want to, I mean, if they want to get a higher grade, I don't think it actually matters too much for me. But I'm trying to be fair in exam. If they cheat, and they cheat in only themselves because they don't really know the subject. So
unfortunately, I have freshman students teaching a service. So
that's a difficult one, especially if it's mandatory courses. It's almost impossible. I mean, it's so I saw the most ridiculous case was, I think, in Italy, where the lecturers asked teachers to blindfold themselves when taking an exam through Zoom. So they can't actually read anything from the monitor. So it would be an oral exam. But so American system could be actually quite good when you have like it's not SAT, maybe SAT type of exams where you have many multiple choice questions, and it's a matter of actually exercise in answering really many questions in a short period of time. So you don't have time for cheating, you know. So it's kind of like you have 1 minute per question, and especially if it's calculus kind of exams, you can create many of them. And you can probably have even a computer generated where you generate many exams. Okay. And if you say have 100 questions and 20 minutes to answer it, I mean, you don't have, if you start cheating, you kind of miss out on many questions. So
that's an idea. That's very nice. Okay, thank you. Otherwise, how are you doing?
Oh, I'm fine, thank you. So missing out a bit on Olympics because it's a bit wrong time for me. So I'm currently in London. So yeah, I just can see in the morning like 1 hour of Olympics, but otherwise quite okay. So, but yeah. So when I joined, Charles University in Prague just when the COVID started. So that was quite a horrible experience for me. So I know how to be a postdoc during the lockdown. So, which is kind of, you don't meet anyone.
Are you visiting London, or are you?
So my parents live in London, so so I came here to visit them for a month. Okay. And I did my PhD in London also in Royal Holloway here.
Okay. Oh. That's very nice. Wow. Yeah. Well, Charles University has quite the reputation. It goes back a ways. So.
Yeah, I think it's we are the oldest in Central Europe, oldest university in Central Europe. I think obviously one cannot compete with Italy, where you have Bologna and Padua and Bologna, I think, are older. Then Cambridge and Oxford are older in UK, and maybe like Salamanca in Spain is older. But I think we tell everyone that we are the oldest in Central Europe. But
the institution I'm at is fairly new. It's only about 3 years old. It's a branch of SRM University, and this is started by a private individual. I'm told it goes back a couple of decades. This is just a branch, but they were trying to be ambitious and getting, you know, emphasis on research and high quality. I'm not sure how things are going to work out, but you know, it's new. They're building it out. The idea was that they split a part of India into 2 pieces. So we have a new capital for a state called Andhra Pradesh. And the new capital is supposed to be, actually, you could see where it was supposed to be from the housing here. But there was a new political party that came in, and apparently their philosophy was wealth and money is like manure, you got to spread it around the field. So instead of having one capital, they want to split the functions into 3 different mini capitals. So there's all sorts of discussion and debate, and people, you know, were striking because, you know, the value of the land that they had gambled on was not what it's supposed to be. I'm unsure what's going on, and the university, you know, is going to just have to adjust its direction, but we'll see. You know.
So is it similar to Tata Institute or not?
So to which?
Tata Institute.
No, not that. Not that prestigious, but they were going to try, and it's a private university instead of a state institution. So maybe Professor Bayer knows more, but being private, they felt that they could avoid some of the difficulties that some of the state institutions have, but still try to pursue excellence in research. There are a number of other facilities in the SRM university system. I'm not too familiar with them, but apparently, you could probably correct me, others could, but they produce a lot of the computer science engineering students. And it seems to be a bit of a industry here where you develop the, undergraduates in computer science, and they get jobs in various companies. Some of them are transplanted from the States, and some of them are, Indian. And some of the best students, after a couple of years, end up in the United States, Silicon Valley and all that. So, and they've had apparently a fair amount of success. Okay, certainly not all the students, but some. So this seems to be, the niche for this institution. How it'll work out, I don't know. I mean, I originate in the States, and I was on the downside of it when when they changed their policies and essentially decided to take, toss American talent aside and take a talent from all over the world. Okay, but that's the way life is. So I end up teaching over here in India.
And how long have you been in India for? 3 years or not, or longer?
No, about 2.5 years, almost 3, not quite.
Okay.
Hello, 1 second. So it's like past, 8 minutes past 4:20. So maybe you can start, and after the talk, we can take it forward.
Oh, definitely. Yeah.
Okay. Then I should announce the talk, I think. Yeah, it was an interesting conversation, but okay, we should start with the talk now. Yeah, that's the last talk in this afternoon session. The speaker is Pablo Yatsina.
It's difficult one.
Okay, yeah.
It is correct. Thank you.
Good. Yeah, thank you. From Charles University in Prague, and he will talk about universal quadratic forms over number fields.
Okay. So thank you a lot for inviting me, and thank you for the scheduling. So the talk really works well with the previous 2 talks. So there's some few distinct differences between this talk and the previous talk. So definitely I will talk about quadratic forms, but unlike in previous talk, I don't really care too much about how many times I represent a given natural number. I just care about instance at least representing it once. That's one difference. And the bigger difference is that quadratic forms I will be considering, at least in the end of the talk, will be the quadratic forms over number fields. Okay, so nevertheless, it's going to be a really friendly talk, and I'll try to actually describe everything. So it's going to be an easy going talk, hopefully, for all of us. So let us begin. So by integer quadratic form, I mean we take integer symmetric matrix. We take symmetric matrix A with integer coefficients such that the diagonal is even, right? So, and then our quadratic form is Q of x, where x is just an integer vector in, well, it's just an indeterminate in the, it's a vector in the indeterminants, and we take a half of it. So diagonal becomes 1. Diagonal becomes uneven now, or not necessarily even. And so this is our integer quadratic form. And in a special case, when this matrix, when it divided by 2, is actually integer matrix, also we say this quadratic form corresponding to this matrix is classical quadratic form. So as I mentioned, that we are interested in representation by quadratic form. So the question is that given some integer n, we ask a question whether there exists a vector in dimension d, integer vector such that q of d equals to n. So it's a classical defined problem. And let us mention some of the classical also, or well-known example of this. Okay. So one of the examples, which all of us met probably in high school, is that Pythagoras triple. So this we have x squared plus y squared, and we ask when these two squares add up to be another square. So like 3, 4, and 5, we would get a square here. Another problem which is studied much more and much more complex is Pell equation. So it's the Einstein equation of a form x squared minus d, where d is some integer, y squared. So x and y are indeterminate, and we want it to be equal to plus or minus 1. So this again is a highly studied question. Then we have a generalization of our first example, where instead of asking about having the square as a solution, we just ask which integers are represented by all represented as sum of two squares. And so this is known as, well, it's known as Fermat two squares, but in reality it was Girard who first studied it, and actually Euler who proved it. And finally, we have this last example that we know that any totally positive, any positive integer or any natural number is represented as 4 squares. So it's a classical 4 squares result by Legendre. And so what do we know? So when one studies quadratic forms, one can study a local global principle, so to speak. So local global principle says that if a natural number is represented, if a quadratic form represents n over real numbers and over every periodic numbers for all primes p, then it's represented over q. So it's a local global principle. So it's sometimes called Hasse-Minkowski principle. Unfortunately, this doesn't really hold if we consider forms of rational integers, right? So for rational integers, we have example of a quadratic forms x squared plus 55y squared and 5x squared plus 11y squared. So these two quadratic forms, so we're going to say binary quadratic forms, they represent the same integers locally, but globally we know we can easily check that x squared plus 55y squared doesn't represent the 5 if we consider only x and y to be integers. So as we can already see that for integers, the situation is slightly more difficult. However, if we allow our quadratic form to have sufficiently many variables, or sometimes throughout the talk, I'm going to say the rank of the form. So if the rank of the form is 4 or 5, so 5 is easier, but 4 is okay under certain restrictions, then the result of Tartakovsky and Klosterman tells us if for given quadratic form with more than 5 variables, let's say, if the quadratic form represents integer locally and this integer is sufficiently large, then it's represented globally. So this is kind of results with 5 and 4 variables, and it's kind of for us naturally leaves the question what happened with 3 variables. So in the case of 3 variables, it's generally really difficult. And one of the prime examples of this is this Ramanujan ternary form. So it's x squared plus y squared plus 10 z squared. So Ramanujan noticed that this form represents every odd integer except for the first, I can't really count really that fast, but nevertheless, it represents all the integers 3, 7, 21, doesn't represent, excuse me. It doesn't represent 3, 7, 21, and up to 679. And he conjectured it doesn't represent, it represents all other odd integers. So later it was also found out that this form doesn't represent 2719. And this is so-called Ramanujan's ternary conjecture, which says that this form x squared plus y squared plus 10 z squared represents all odd integers other than this, highlighted in red. And this was actually proven, but only under the generalized Riemann hypothesis. And it's, we can say, a recent result, so it's 24-year-old result. And so what I want to talk today about is the universal forms. So we say the quadratic form is universal if it represents all natural numbers. So it represents all natural numbers. So example of this is that this ternary form x squared minus y squared minus dz squared, where d is not divisible by 4. So this form is also indefinite, and so we say the form is indefinite when the corresponding matrix is indefinite. And we generally, because of algebraic side and analytical side of indefinite forms is much better understood, we more or less will focus today exclusively to a positive definite case. So we will just focus on quadratic forms where the corresponding matrix, so the symmetric matrix I introduced in the beginning, where this matrix is going to be a positive definite. Okay, so in positive definite case, we know that there doesn't exist universal positive definite ternary form, meaning that you need more than 3 variables to represent all natural numbers. That's number 1. And number 2, as I mentioned before, the Legendre show that 4 squares is universal, meaning that any natural number is represented by 4 squares. And Ramanujan and Dixon classify all the diagonal forms with 4 variables. And by a diagonal form, I mean just a form where the corresponding matrix is diagonal matrix. Okay, so that's what we know. So, so one who knows slightly about Ramanujan knows he lived in 20th century, early 20th century. So that's kind of what happened. And then there was a recent breakthrough in late 20th century. So this so-called number theorems. And so we begin by theorem 15. So 15th theorem was proven and conjectured by Conway. So Conway actually had this idea about which he shared with his students. I think it was his quadratic form course or something like that. And the conjecture was that there exists a finite list of integers which quadratic form represents. And if we just check this finite list of integers and the quadratic form represents this finite list, then it represents all natural numbers. And so this is currently known as theorem 15. And so it says if a classical positive definite quadratic form is universal, and it's if and only if it represents these integers between 1 and 15, right? So you need to represent 1, 2, 3, 5, 6, 7, 10, and now 14 and 15. And so I want to highlight that here we have a classical idea. So we do need classical in this case. So if you take away from classical and just ask for the form to be integral, then it becomes quite more difficult. And so this is known 290 theorem. So it was proven by Bhargava and Hanke. And he said that if we just take away this classical restriction, that we need to actually check all the integers, not all the integers, but integers between 1 and 290. That's hence the title of the theorem. Actually, Bhargava simplified the proof of theorem 15, which is quite neat. However, for the 290 theorem, so one can say that theorem 15 has quite an elementary proof. However, 290 theorem uses much more advanced tools, and it's although I wrote here it was proven in 2011, the paper never got published really. So it was accepted. However, there's a computational part to the proof which both authors tried to simplify it and kind of never got to it. Nevertheless, they also suggested that for positive definite quadratic form, we can consider any infinite set S. And for any infinite set S of natural numbers, there exists finite subset such that we can check only this finite subset and get this similar to 290 theorem proof. Right, so and here's an example of this result. So it's a 451 theorem by Rose. So this theorem assumes that given this 3 ternary form, so assume that this 3 ternary form represent all odd positive integers. So if this is true, which is not known really, but it's I think conjecturally it is true. So if these three forms represent all odd integers, then any positive definite integer quadratic form represents all odd integers, if and only if it represents all these integers between 1 and 451, obviously odd integers. So that's kind of, so it's definitely not everything that is known for rational integers. Nevertheless, it's kind of a flavor of results there are. And so, so I'll try to focus on number fields. So quadratic forms over number fields. So let us maybe quickly remind ourselves what are the number fields. So by a number field, I mean generally a number field, I mean just finite extension of rationals. So we just take Q, our rational field, and adjoin some algebraic number or algebraic integer. And so, so instead of studying forms over rationals, we study the forms of the ring of integers in the rationals, right? So we replace our integer z by some ring of integers OK, where k is our number field. So here's a few examples which all of us saw many times now. So if we adjoin imaginary number to integers, we get our Gaussian integers. If we adjoin this third root of unity to z, we get Eigenstein integers. And more generally, if we adjoin any root of unity to q, we get cyclotomic numbers. And so cyclotomic numbers generally is quite a useful number field family to study because of the nice structures they do have. So working with number fields is not really much different than working with rational integers. However, there's a few difficulties. So one of the difficulties is that generally we can't assume we have unique factorization. And it does actually possess a problem when one works with lattices. So I won't actually mention it too much, but then when one works over the rational integers, we can assume we have free bases, and that's not necessarily the case when we work over number fields. So not one problem. Second problem, which is again is something I will mention later, is that we cannot assume that our integers have power bases, integral power bases. And so this is a famous Dedekind case of when the number field doesn't have integral power bases. And so one of the beauty of working with cyclotomic numbers is that ring of integers always have power bases, right? So what it means is that this with adjoint square root of unity is actually exactly the ring of integers over the cyclotomics, as opposed to just some subring. Okay, so now we have number fields, and I can probably now now define what I mean by quadratic form over number fields and what kind of problems you want to deal with here. We will restrict to totally real number fields, and by totally real number fields, I mean the number fields such that all the embeddings of our number field is actually in real. So we have embeddings into our number field in the C or R, complex numbers or real numbers. And the number fields I will restrict to are going to be only where we have embeddings only in R. And so the really simple examples, and probably the first example one always considers, are the real quadratics. So real quadratics, as we saw in previous two talks, is just when we adjoin a q square root of d, where d is a positive square free number. So that's a really good case. And another case is a maximal real subfield of cyclotomics. So here, zeta n is just root of nth unity, and we adjoin to q the nth unity plus its inverse. So that's a maximal real subfield. And more generally, for totally real number field, is just Q adjoined with alpha, where the alpha is a minimal where the alpha is a root of polynomial such that all of the roots of this polynomial are real numbers, or the minimal polynomial of alpha has only real roots. So that's generally what we're gonna work with here. Now we need also define what we mean by totally positive integer. So we take algebraic integer alpha, and we say that alpha is totally positive if all the embeddings of alpha are positive numbers. And that's kind of the reason why we want to work with totally real number fields, because we want to have this definition. And by universal form, we will mean that Q is universal form of O. We say it's universal if it represents all totally positive integers and if it's a totally positive definite. And what I mean by totally positive definite, I mean that if we take the corresponding matrix and we consider all of its embeddings, then each of the embedding will be a positive definite matrix. So in each embedding, we're going to get some matrix which is going to be a positive definite. Okay. So now let us maybe tell what is known for these cases. So one of the results which uses a local global principle, it says that sum of 3 squares is universal over the Q adjoint square root of 5. So this is the result of Maas. And so what Maas did, he showed that 3 squares has class number 1. And then it is known that 3 squares locally are universal over Q square root of 5. And so now here was a local global principle is used here. That's a result of 1941. Then Siegel came and showed that the sum of squares are universal over the totally real number field, if and only if this number field is either Q adjoint square root of 5 or rational numbers. Right, so basically for every other number field, there exist some integers which are not represented as sum of squares. So as you can see, this actually, there's not a big gap between the two results of Siegel and Maas. We also have that any ternary quadratic form represents sufficiently large totally positive integers which are represented locally. This is more recent result, and this is more in the shape of the result of Klosterman and Tartakovsky. Something to mention about this result, again, the proof is never was officially published for this result, and I'm not sure if it will be published, but I think at least the result of this shape for the sum of squares is known. So it is known that 3 squares represent all sufficiently large square-free integers if they're represented locally. Something to mention here also is that this sufficiently large is usually measured in terms of norm or trace. And for this result specifically, the sufficiently large is ineffective. But this result is specifically for totally real number fields. So it is known, Chan, Kim, and Raghavan, they classified all the quadratic number fields where we have ternary forms, which are universal. And we can already see the big difference between studying the quadratic forms over the rational integers and number fields. So over rational integers, if you remember, there do not exist ternary forms, and over number fields that do exist. So at least in real quadratic cases, these are the only 3 number fields where this is possible. And there doesn't exist ternary universal quadratic form over real quadratic fields of odd degree. And that's a result of Ernest and Khosravani. And this result using some local theory. So this is using I forgot the name of the So it's using local theory, but I forgot the name of the symbol you used to prove that. Okay, so clearly we see that for having ternary form, which is universal of a real totally real number field, the degree of the number field need to be even. And this is conjecture of Kitaoka, which says that only finitely many number fields over which there exists universal ternary form, right? So he says that although they are possibly, obviously they exist ternary quadratic forms which are universal, however, those cases are quite rare and they're finite. So let us maybe focus a bit on more a tangible case of quadratic number fields. So over real quadratic number fields, so what is known is that there exist infinitely many number fields over which there exists universal form in 8 variables, right? So 8 variables, if you have form in 8 variables, there are infinitely many number fields quadratic. So all is we need to do is need to make sure that n squared minus 1, so n here is an integer. We want that this number n squared minus 1 is square free. So as soon as we have this n squared minus 1 is square free integer, then every number field q adjoint square root of n squared minus 1 will have a universal quadratic form in 8 variables. And so the result is really nice. So the idea is really beautiful. It was proven by Kim in 1999. And the recent result shows that actually by Kim and Park, that there are only finitely many totally real quadratic number fields over which 7 variables is sufficient to be universal, right? So it's kind of, we have finitely many cases up to 7 variables and infinitely many cases with 8 variables and more. This is known, and as a result of Kala, Bloma, and Kala, we show that for any integer, positive integer, there exists infinitely many universal quadratic forms that do not admit a quadratic form of rank m. So all that means is that there doesn't exist bound based on the degree of extension on the number of variables you need to represent all the totally positive integers in the real quadratic number field. Okay, so just to maybe highlight what is the issue here. As I mentioned before, that using squares is not sufficient. So there exist integers, totally positive integers which cannot be represented as squares. So a really useful tool to deal with representation is actually kind of try to understand totally positive integers. And one really nice tool is this considering indecomposable integers. So we say the totally positive integer is indecomposable if you cannot write it as a sum of 2 totally positive integers, right? So example of this would be, for example, 1. 1 is always indecomposable, as 1 you cannot write as anything smaller. And more generally, any totally positive unit is indecomposable. So it is known that there's only finitely many indecomposables up to multiplication by a unit, so or square of a unit. And generally, the structure of indecomposables is well understood in real quadratic number fields. And all this theory about understanding the structure is based on using quadratic continued fractions. And that's how many of these bounds previously were found. So maybe not this result, but the latter two are actually found by studying indecomposable integers and try to understand the structure a bit better. And so what's happening in higher degrees? So by higher degrees, I mean when we consider number fields of a higher degree. Well, in that case, we don't really understand indecomposables that well. So Kala and Svoboda found some lower bounds for the number of variables in powers of 2 number fields. And they were considering adjoining a lot of square roots to the number fields. So they get these multi-quadratic number fields. And the idea is, again, finding the number of these indecomposable integers. And So the gist of the proof of or gist of the tactic is that you show that number field have a lot of indecomposable integers, and you want to force your quadratic form to represent all of these integers. And then you show that to represent these indecomposable integers, you need many variables. And so when you have this multi-quadratic forms, this is possible. In recent result, Kala and Tinkova studied Shintani decomposition also to show that for cubic fields, you also have this nice bound for the number of variables for universal forms. And finally, for number fields divisible by 2 or 3, of degree divisible by 2 or 3, Kala recently also had some bounds for the number of variables needed. So I want to present to you a slightly different result, maybe, for higher degrees. So first of all, we need to work with monogenic number fields. So number field is monogenic when we have integral power bases. So it's monogenic when the ring of integers is exactly z adjoint some algebraic integer alpha. And this is not always the case. Nevertheless, when it is the case, we say the number field is monogenic. And we also need to restrict to number fields which are primitive. So by that, I mean that there's no subfields, no proper subfield between K and Q. So for example, any number field of prime degree will be primitive. And so this is one of the results I'm going to present to you today. So given some D and R natural numbers, there are only finitely many totally real primitive and monogenic number fields. So basically number fields satisfying these conditions that have units of average signature and universal form of rank D defined over them. So what does this result tell us is that if you have units of average signature, monogenic number field and a primitive number field too, then the rank of universal form is not bounded. So it grows. There's only finitely many forms of given bound. And so let me just give you idea of the proof and why we need these conditions. So first of all, if you have a monogenic number field, our ring of integers is at alpha. And then the codifferent of this number field can be represented as some fractional ideal, delta times our ring of integers. And now if we have units of average signature, we can make sure that this delta is going to be totally positive definite. Excuse me, it's going to be totally positive. And so now we correspond all the elements in a codifferent of trace 1 to certain interlacing polynomials of our minimal polynomial of alpha. So I will not explain exactly what these interlacing polynomials are. Nevertheless, if we assume that number field is primitive, then we can show that number of these interlacing polynomials grows with the discriminant of this minimal polynomial of alpha. And so in particular, given that the number field is monogenic, it will grow with the discriminant of the number field. So long story short, it says that as the discriminant grows, the number of interlacing polynomial grows. And so the number of these elements of trace 1 also grows. Now we consider we take our quadratic form, which we assume to be universal over this number field, OK, and we multiply it by delta and take a trace of it, right? And so we take exactly this delta from the codifferent, and by the definition of a codifferent, we know that it's going to be integer quadratic form. And by taking a trace of this quadratic form, we increase. So if Q has rank R over OK, then it's going to have a rank RD over rational integers. All right. So by taking this trace, we increased rank of our form by multiple of D. And so now, because we know that number of interlacing polynomial grows and number of these elements of trace 1 grows, each of this element gamma in a codifferent will correspond to the minimal vector in our quadratic form over rational integers. And the maximal number of these minimal vectors of positive definite quadratic form is bounded by rank, right? So this is so-called Kisin number. And so in particular, if the discriminant grows, at some point the rank needs to grow also. And that's basically the idea of this proof. Now, so this, we just work with general quadratic form, but we can simplify the question slightly. So instead of considering any quadratic form, we can consider quadratic form with integer coefficients. So we take a form with integer coefficients and ask when this form with integer coefficients, which we're going to call the Z form, is universal over a given number field. And so example of this is exactly the sum of squares, because the sum of squares is a Z form, and we know it's only universal over the rational integers or over the Q adjoint square root of 5. So another example of this Z form is this form of rank 4, which was shown to be universal over the Z adjoint 1 plus square root of 5 over 2. So it's exactly this case where we have a Q adjoint square root of 5. And so in a recent paper, we showed that there doesn't exist except that finitely many cases in the following degree. So 1, 2, 3, 4, 5, 6 is missing, and 7, with a condition on the codifferent. There doesn't exist Z universal forms defined over these number fields of these degrees, unless this number field is either Q adjoint square root of 5, or this maximal cyclotomic number field. And over this maximal cyclotomic number field, we found this quadratic form which is universal, Z form which is universal. So now, when you work with Z forms, we can think of that taking a quadratic form and we extend its scalars. And so naturally, one works with tensor products. So given two Z forms, Q and P, we define a tensor product. So we take Q tensor P, and we take a V and tensor V W. And so this product will be Q evaluated at V and P evaluated in W. So what we have is that minimum of Q tensor P is less than or equal to minimum of Q and minimum times minimum of P. And the forms, when this is exactly equal, are called the forms of E-type. So we say that form Z, Z form Q is of E-type if for every positive definite form P, if its tensor product satisfies the minimum of Q tensor P equal to minimum of Q tensor minimum of P. So these are the forms of E-type. And so here's what's known for this forms of E-type. So first of all, the Kitaoka showed that all forms of rank between 1 and 43 are of E-type. And Thompson and Conway found example of a form of not E-type for the rank 248. So between ranks of 44 and 247, there are possibly forms which are not of E-type, but it's not known. It is, however, known that for every n greater than 292, there exists a form not of E-type. This is was proven by Steinberg. And possible examples of this form of E-type, not of E-type. So the candidate for the form of rank 84 and 96. So this form of 96, that would be extremal self-dual case of minimum. So it's even self-dual lattice with minimum 10. That would be a possible example, but it's not known whether they exist or not, these two forms. So let me just finish now by giving the idea for this proof of theorem, which is not too far different from what I mentioned before. So we consider a positive definite quadratic form so we let P to be the trace of delta x squared, where delta is some element in a codifferent, positive element, totally positive element in the codifferent. And we assume this form is of E-type. So it's going to be a rational integer form. We assume it's of E-type. And based on this assumption, we can say something about these elements in the codifferent. So we can restrict them. For example, we can say they should be units. And then we use this result by Siegel. So for the dimension, for degrees 2, 3, 4, 5, and 7, and that's exactly why we don't have 6, we know that Dedekind zeta function evaluated at 2 is this form. So the notable parts here is that this BD is a rational integer which doesn't depend on the number field, but it just depends on a degree. We have here we have here discriminant of our number field, and we have here the sum which depends on these elements of trace 1 in a codifferent. And so using this form, we can bound the discriminant of a number field over which we could have the universal Z forms. And so basically, as soon as the discriminant is too large, we know that we can't have universal Z form, and so it leaves us finitely many cases to check, and we check those finitely many number fields for universal Z forms, and that's completed the proof. And so up and coming result we're going to have is that for each degree D, there are only finitely many totally real number fields of degree D with the universal Z form. So I think I went rather fast, so I presume there's room for many questions. So nevertheless, thank you for listening.
Thank you very much for the interesting talk. Are there any questions? Yeah.
Is there any general way to find possible cubic totally real fields besides monogenic that might have universal quadratic forms?
So it is possible. So, but it becomes really difficult. So I mentioned here, where was it? So recent result by Kala and Tinkova. They do study this simplest cubics, which are monogenic and which are nice. And so the problem becomes that, I mean, there are many problems. So they're using Shintani units there and try to understand all the indecomposables this way.
Okay.
Given some sort of bound on a universal form is easy, but given a lower bound is really hard generally, right? So it's because if you find all the indecomposables, and that's we know there's finitely many of them, and there's a bound on the maximal norm of indecomposable based on the Brunot result. So this based on regulator. So it's theoretically it's possible, but practically it's really difficult. And
okay.
So just working with monogenic is just much more practical in some sense.
Okay, fine. Fine.
Okay, thank you. One question from my side. You mentioned this conjecture by Ramanujan at the beginning. So this particular ternary form represents all numbers except
no, all odd numbers.
All odd numbers. Yeah, precisely. So do you know how he came up with that? So I'm just wondering.
Classical way. I think he probably computed it. And then he said that this form represents. So this form has class number 2, and so one can check locally that this it represents everything odd. However, you don't know which of the two forms going to represent all the odd numbers.
Okay.
And so the Ono and Sundararajan proved it, but it's quite a difficult proof. So it assumes a Riemann hypothesis, generalized Riemann hypothesis.
Okay. And this number 2719 was found later. That was not in
yeah, so he just missed it. So he just by computation he missed it. So he didn't conjecture it. He stated it, and I think later it's got conjectured that it should be the case. I mean, for him, I think I forgot the name of the paper where he wrote that this interesting case, and this form appears not to represent only these integers. And so this is kind of the form where he studies, maybe he studied theta function paper. I forgot the name of it, ternary theta function corresponding to ternary forms. But please don't quote me on that. But it's a well-known paper, I think, by him. Or, well, which paper is not known by him, but so he didn't really conjecture it per se. He just stated it as an observation, and later it got conjectured as a problem by him.
I see. Okay.
And it's got its own Wikipedia page, so, so it's somewhat important.
Oh, I see. Yes. Okay, interesting.
I also have one question in similar when that 15 conjecture also it looks little magical. So if you can say that why something like that is believed.
Well, so the way you do it actually, so the 15 is almost magical. Is the way you kind of you grow. So you start with a form of rank 1 and you see everything it represents. And you kind of know what you want to represent. So you always want to represent. So you order, first of all the integers you want to represent. And then you start with a form. So you want to represent 1, first of all, to represent all natural numbers. So you always need to start with x squared, right? And now you want to add, check the first integer you don't represent after that. And so the next integer you don't represent 2. So you want to add extra variable now, and you want to represent 2 in this extra condition, right? And so you grow this way. So you have 2 examples when you're going to grow with 2. And then you're going to have 2 different forms you can consider. And then you see the next integer you don't represent, the next largest integer you don't represent.
Okay.
And
that's why
grow like that, and eventually you kind of get a tree of forms you have. And eventually you see that every path you take, you're going to have universal form. And all you do then is just check which numbers you had to represent in each step, right? To check if you represent. And what you're going to find is this integers exactly you don't represent. 1, 2, 3, 5. So as you can see, the squares are missing, right? Because if you represent 1, you represent 4, and so on. So I suppose the hardest part here is conceptually to come up with the idea that is possible, and that's kind of Conway-esque theorem. So but after that, I think the proof is quite nice and easy. But obviously, one needs to come up with a problem first.
Yeah, this is really.
It is magical in some sense. So it's. And so there are attempts to do this for the number fields, but it becomes quite more difficult because that's even difficult way of actually how do you order elements, in a rational way. So that's a difficult part also. But for certain number fields, so Q adjoins square root of 5, which is also in some sense really special number field, I think it wasn't. It was actually achieved. So there exists this similar result for this number field.
Okay, thank you very much.
Oh, thank you for the question.
Thank you. Are there other questions? It looks like there are no further questions. Yeah, then let's thank the speaker again for a very nice talk.
Thanks a lot. Thanks a lot.
Thank you.
Hopefully, I wasn't too inspired by athletics today and didn't go too fast. But
no, it was fine.
Okay, thank you.
It was fine. Mhm. Yeah, then this is the last talk for today. And yeah, tomorrow the first talk will be at 10 a.m. again. Good. Then I say now bye-bye.
Okay.
And
Thanks
see
for the
you.
invitation.
Yeah. And see you tomorrow.
Bye.
Bye-bye.
Yeah, now you can close. Yeah.